Good evening, and welcome to The Sleepy Scientist, your quiet place to drift into rest while still letting curiosity roam. Tonight's video is all about physics facts, hundreds of them, each unpacked slowly and gently, like turning over smooth stones along a riverbank. Where in the world are you listening from? Your bed, your favourite chair, or maybe somewhere entirely unexpected? If you're enjoying these late-night explorations, a like and a subscribe would mean a lot, and for those already subscribed, thank you for being part of this calm little corner of science. If you haven't yet, kindly tap the notification bell so you won't miss the next upload. And here's a small joke to ease us in. Hopefully these facts won't be so fascinating that they keep you awake all night. But if they do, at least you'll slip into tomorrow with a head full of knowledge. So let's begin with a question that will follow you into the first chapter. What hidden patterns of physics quietly link the simplest drop of rain to the most distant galaxy? Tonight's journey is simple. 300 physics facts gathered into steady clusters, each one explained slowly enough to calm the mind while still sparking wonder. Rather than racing from formulas to jargon, this video lets the ideas breathe. Why motion curves, why heat spreads, why light bends, why time itself can flow differently depending on where you stand. Each set of facts is arranged in small groups of 5 to 7, so you can follow along easily, like counting stars in the night sky. The rhythm is deliberate. Mechanics and motion arrive first, followed by energy and waves, then into electricity, light, relativity, and quantum puzzles, all the way out to galaxies and the universe itself. Along the way, familiar experiences like why seatbelts keep you safe, why the sky is blue, or why your tea cools, will rest alongside the grander scales of black holes and the origins of the cosmos. It's a patchwork of the everyday and the cosmic, each piece held together by the quiet logic of physics. So as you settle back and let the words move at their own pace, hold this thought gently. If physics is everywhere, from your heartbeat to the heartbeat of stars, what surprising connections will reveal themselves tonight? Let's start with mechanics, the branch of physics that deals with motion in its simplest form. One of the first distinctions to make is between distance and displacement. Distance tells you how much ground you've covered, while displacement is more precise. It measures how far you are from where you began, and in which direction. You could walk 10 city blocks in a loop, and return to your front door. Your distance travelled is 10 blocks, but your displacement is 0. That difference matters in physics, because displacement, not distance, ties directly into other concepts like velocity and acceleration. From there, it's only natural to talk about speed and velocity. Average speed is a comfortable, straightforward measure. Total distance divided by total time. Average velocity, however, is trickier because it uses displacement instead. Imagine driving 20 kilometers out of town and 20 kilometers back again in 1 hour. Your average speed is 40 kilometers per hour, but your average velocity is 0, because you ended up exactly where you started. It's a reminder that physics is concerned less with how much effort you put in, and more with the net effect of your journey. When acceleration is constant, things get more interesting. Position over time no longer makes a straight line but a parabola, the same elegant curve traced by a tossed ball or a launched arrow. Equal amounts of time don't yield equal changes in height or position, because velocity itself is changing steadily. That's why a falling object covers more ground in the last second of its drop than it did in the first. This graceful mathematics, so often tucked into high school equations, actually governs everything from playground slides to planetary orbits. But there's another layer often overlooked, the rate at which acceleration itself changes, known as jerk. You feel jerk every time a bus lurches forward, or an elevator starts too abruptly. It's not just acceleration that matters, but how suddenly that acceleration appears or disappears. Engineers design systems with jerk in mind. Roller coasters carefully manage it for thrill without injury, while robotics smooth it out for precision and durability. Comfort, safety, and efficiency often come down to this subtle measure. Relative motion adds another wrinkle. Your velocity always depends on who is watching. Walk along a moving walkway in an airport, and to a person standing still, your speed is your walking speed plus the walkways. Cross a river, and you'll need to aim upstream so the current doesn't carry you away. That's vector addition at work, blending your swimming velocity with the river's. Pilots do the same with crosswinds, adjusting headings so the true path over the ground is straight. There's no such thing as absolute motion. Everything is relative to a frame of reference. Finally, motion graphs bring all these ideas into focus. A line on a position-time graph has a slope that shows velocity. A line on a velocity-time graph has a slope that shows acceleration, while the area beneath it tells you the total distance travelled. Even acceleration-time graphs tell a story. The area under the curve gives the change in velocity. These simple diagrams turn the language of calculus into something you can see at a glance, revealing the hidden patterns of movement whether you're watching a bouncing ball or a spacecraft on its way to the stars. If you launch a ball in a vacuum at some angle above the horizontal, there's a neat symmetry waiting for you. The horizontal range at an angle theta is the same as the range at 90 degrees minus theta, provided the launch speed is the same and the launch and landing heights match. A gentle lob at 30 degrees and a steep shot at 60 degrees travel the same horizontal distance because the steeper shot trades longer airtime for less horizontal speed, while the shallower shot does the opposite. The product conspires to match. This is why there isn't one magic angle for distance below 45 degrees or above 45 degrees. Pairs around 45 degrees are twins in disguise. Only at exactly 45 degrees does the range reach its maximum for a given speed and equal launch and landing heights. How long a projectile spends climbing versus falling depends on where it starts and where it finishes. If you launch and land at the same height, the time up equals the time down, a perfect mirror about the peak. Velocity loses the same amount on the way up that it gains on the way down under constant gravity. But change the landing height, and the mirror cracks a little. Fire from a cliff, and the descent lasts longer than the ascent. Launch from a valley to a hilltop, and the ascent takes longer than the descent. The clock follows energy. Higher endpoints demand more potential energy and more climb time. Lower endpoints return that potential as extra speed and extra fall time. Air has opinions, and those opinions break the clean symmetry of vacuum motion. With drag, the upward trip and the downward trip are not equal and opposite. Going up, the projectile is slowest near the top and drag is modest. Coming down, gravity and drag often align in direction near terminal speed, leading to a different balance of forces. The peak shifts closer to the launch point than vacuum math would predict. The landing spot comes up short, and the path is no longer a perfect parabola. Shapes, spin, and speed all matter. A streamlined dart slices the air more kindly than a crumpled ball of paper, and a back-spinning ball can even generate lift that stretches its journey. Sometimes the odd forces you feel aren't forces at all, but artifacts of your point of view. In a rotating or accelerating frame, like a merry-go-round, a car turning sharply, or Earth itself, your equations sprout fictitious forces. Centrifugal pointing outward from the rotation axis, and Coriolis nudging motion sideways. Stand at the equator, and a freely moving air mass is deflected to the right in the northern hemisphere, and to the left in the southern hemisphere by the Coriolis effect, shaping trade winds and ocean currents. Sit in a turning car, and you feel pressed outward, but there's no new interaction. Your body wants to keep going straight while the car turns under you. These forces aren't fake in their effects. They are bookkeeping terms that make Newton's laws work inside a non-inertial frame. When a frame rotates, accelerations pick up extra pieces that describe how position and velocity look from that spinning vantage point. The relative acceleration of a point includes a term that points inward, proportional to the rotation rate squared and the distance from the axis, often described as minus omega cross r, and a term that is twice the cross product of the rotation vector with the velocity relative to the rotating frame, which is the Coriolis part. The inward term explains why objects seem to be thrown outward, but are mathematically tethered inward. The 2 omega cross v term explains why moving things get sideways nudges in rotating worlds. Pilots, sailors, meteorologists, and even amusement park designers quietly account for these terms so paths come out right, instead of gently curving somewhere unexpected. There's a clever way to make dynamics feel like statics. Slip everything that smells like inertia to the other side of the ledger and call it a force. That's D'Alembert's principle. You take the real external forces acting on a system and add an inertial force equal to minus mass times acceleration, and then you balance the books as if the total was 0. Suddenly a moving system can be analysed as though it were in equilibrium, which opens the door to powerful methods from statics, constraints, and virtual work. It's like flattening a complicated problem into a clean accounting exercise. The motion is still there, but it's encoded in those inertial terms so you can solve for unknown reactions and tensions with calm, steady algebra, rather than chasing every twitch and turn directly. Work in physics sounds straightforward. It is simply force multiplied by displacement, but the details reveal subtleties. When a force is conservative, like gravity, or an ideal spring, the work done only depends on where you start and where you finish. The path in between does not matter. Lift a backpack straight up 3 meters, or drag it up a winding staircase 3 meters higher, the work against gravity is the same. But when the force is non-conservative, such as friction, the path matters. Push a box across a floor along a short direct line, and you do less work against friction than if you detour around the room before arriving. The energy lost as heat is tied to the distance slid, so suddenly the route becomes as important as the start and finish. Power is the rate of doing work, and it too has an interesting story. For engines, motors, and even human muscles, maximum power does not happen at either extreme of load. A motor running with no load spins quickly but does little work per turn. At the other extreme, when the load is far too heavy, it hardly moves at all, and again produces little useful output. Between these extremes is a sweet spot where both speed and force balance to deliver maximum power. This principle of matching is found in electronics as well. A power source delivers the most energy when the resistance it feeds is matched to its own internal resistance. Whether mechanical or electrical, nature often rewards the middle ground. Potential energy offers another layer of subtlety. Its value can never be pinned to a universal 0. Only changes matter. Set the ground as your 0 for gravitational potential, and a roof will have positive potential energy. Or shift your 0 to the roof, and now the ground sits at negative potential. Neither choice is wrong, because physics only notices the difference between 2 positions. Springs behave the same way. Stretch it from its relaxed length, and you store energy. But where you decide to write 0 on the ruler is entirely up to you. The constant offset never affects the work done, which is why equations focus on changes, not absolutes. When forces are conservative, they can be described by a potential function. Mathematically, the force is equal to the negative gradient of the potential energy. In plain words, this means the force always points downhill in the landscape of potential, nudging systems toward lower energy. Imagine a marble resting on a hill. it naturally rolls toward the valley because that is the direction in which potential energy decreases most steeply. The minus sign simply reflects this tendency. If you could map every potential energy surface, gravitational, electrical, or elastic, you would see the future of motion etched like contour lines on a topographic map. Mechanical advantage is one of the oldest tricks humans discovered. Levers, pulleys, and gears let you trade force for distance. Push with a small force over a long distance, and you can lift a heavy load through a short distance. Push with a large force over a short distance, and the load moves farther. In the ideal case, where there is no friction or bending losses, the input energy always equals the output energy. You cannot get more energy out than you put in. What these devices really do is let you choose how that energy is packaged, either as a small push over a long stretch or a big push over a short one. Efficiency sets the boundary between the ideal world and the real one. No machine converts 100% of its input energy into useful output. Some energy escapes as heat through friction, some is lost as sound or vibration, and some radiates away in ways we cannot harness. Steam engines are limited by the temperature difference between their hot and cold reservoirs. Electrical transmission lines inevitably waste a portion as heat. Even the human body is only about 20 to 25% efficient at turning chemical energy from food into mechanical work. These ceilings are not mere imperfections in engineering. Many of them are rooted in fundamental laws like the second law of thermodynamics. Efficiency is the measure that reminds us of those limits, marking the gap between the dream of perfect conversion and the reality of a world where energy always finds ways to slip into other forms. In a true explosion that is isolated from outside influences, the total momentum is conserved because the net external impulse is zero. Think of a firework shell drifting in still air at some velocity. Just before it bursts, its momentum is mass times velocity. When it fragments, forces between pieces are internal. They push on each other in action, reaction pairs that cancel in the total. The vector sum of all fragment momenta after the burst equals the shell's momentum just before it. In symbols for narration, total momentum after minus total momentum before equals zero when the external impulse is zero. Another way to say it is that impulse equals the integral of force over time, and if the external force is effectively zero during the brief explosion, the centre of mass motion does not change. How bouncy a collision is gets a precise dial called the coefficient of restitution, spoken as E. It is defined as relative speed after impact divided by relative speed before impact, measured along the line of collision. When E equals 1, the encounter is perfectly elastic. Kinetic energy before and after is the same, like two ideal billiard balls that ring but do not warm. When E equals 0, the impact is perfectly inelastic. The objects stick together and move as one, maximizing kinetic energy loss while still conserving momentum. Most real-world impacts sit somewhere in between, with a between 0 and 1, which is why a tennis ball bounces higher than a clay lump but not as high as a super ball. Not every collision is a head-on crunch. In a glancing strike, say, a cue ball clipping the edge of a spinning top, or a bat catching the ball off-centre, linear momentum can be converted into rotation because of torque about the contact point. The incoming object delivers not only a shove but a twist. In shorthand words, change in angular momentum equals torque times collision duration. That is, L changes by tau times delta t. Striking off the centre increases the lever arm, so even the same push produces more spin. This is how players intentionally add slice or top spin, and why an off-centre hit can send an object flying with both translation and a lively rotation. Recoil is momentum's way of keeping the books balanced, and it appears even when the launched mass is tiny. Fire a very light pellet from a much heavier launcher, and the launcher still moves backward. Momentum is P equals mass times velocity, so the small mass leaves with a large forward velocity, while the large mass acquires a small backward velocity. The vector sum remains what it was. Energy does not balance in the same sense, because kinetic energy scales with the square of speed. The fast pellet carries a lot of kinetic energy compared with the gently moving launcher. This is why a gas jet can send a spacecraft drifting the other way, even though the expelled gas has very little mass. Momentum, not energy, is the conserved quantity that dictates the recoil. When many objects interact only with each other, their collective center of mass glides as if all the internal pushing and pulling did not exist. Internal forces come in equal and opposite pairs and cannot change the total momentum of the group. The motion of the center of mass depends only on external forces. Say a pair of skaters on frictionless ice push off. They separate, one speeding left and the other right. Yet the midpoint weighted by their masses keeps its steady course. In equations read aloud, total mass times acceleration of the center of mass equals the sum of external forces. If that sum is zero, the center of mass moves at constant velocity regardless of the flurry of motion inside the system. Sometimes a change in motion happens so quickly that nothing has time to bend or heat appreciably. That is an impulsive event, like a rigid stop halting a sliding door or a hammer striking a chisel. During the very short contact time, the impulse, force times time, dominates over gentler effects, and momentum is redirected almost instantaneously. The door's momentum along the track becomes zero while forces at the stop spike for a brief moment. Energy may not be conserved if some becomes sound or heat, but the momentum change equals the applied impulse. In narrated symbols, impulse J equals integral of force over time and equals change in momentum, delta P. By focusing on that impulse, you can predict the new motion without tracking the fleeting details of deformation. Moments of inertia are like the rotational cousins of mass. They tell you how reluctant an object is to being spun. But unlike mass, they depend on the axis you choose. The parallel axis theorem gives a shortcut. The moment of inertia about any axis parallel to one through the center of mass equals the center of mass inertia plus total mass multiplied by the square of the distance between the axes. In words, I equals I subcenter plus md squared. That means if you know how a disk spins around its center, you can instantly calculate how it spins around an edge. This trick saves mountains of calculation, and it's why physicists can rattle off values for new axes without doing fresh integrals every time. For flat planar bodies, there is another gem, the perpendicular axis theorem. It states that the moment of inertia about an axis perpendicular to the plane equals the sum of the moments about two perpendicular axes lying in the plane and intersecting at the same point. In words, ISO equals x plus IY. Think of a thin plate lying in the XY plane. Its resistance to spinning about the z-axis is exactly the sum of its resistances to spinning about x and y. This is a rare case where geometry and algebra meet with a simple, elegant balance. The theorem only holds for flat laminae, but within that world it is powerful, letting you build complex inertia values from simpler ones. Just as linear work is force times displacement, rotational work is torque times angular displacement. When you integrate torque over an angle, you get the total work done on the object. Work equals the integral of tau d theta. That work appears as rotational kinetic energy, which has a familiar looking form, 1/2 I omega squared, where I is moment of inertia and omega is angular velocity. The analogy to 1/2 mv squared is not an accident. It is the rotational echo of the same energy principle. This relationship makes sense of why heavy flywheels or fast-spinning rotors carry so much energy. Inertia or speed increase either, and energy grows rapidly. Rolling friction has a different origin than the sliding friction most people imagine. A rolling wheel, in theory, could move forever without energy loss if its surface and the ground were perfectly rigid. In reality, both deform slightly under load. That deformation absorbs energy as the wheel continually squashes and releases the ground beneath it. The result is rolling resistance, a gentle but persistent drain that explains why bicycles coast better on smooth pavement than on soft sand. It is not the surfaces scraping, but the subtle bending that makes rolling imperfect. Even tiny distortions add up over long journeys, quietly turning motion into warmth in the material. Bearings are one of humanity's great solutions to this problem of unwanted torque losses. By reducing the contact area to tiny spheres, cylinders, or even a thin fluid film, bearings cut down shear forces and rolling resistance within machines. Instead of broad patches rubbing and tearing at each other, only small points or thin layers carry the load, drastically lowering friction. From the wheels on a skateboard to the turbines in a jet engine, bearings are the hidden guardians of efficiency, extending lifespans and conserving energy. The less energy wasted in the supports, the more that remains to keep the rotation alive. Flywheels are where rotational physics turns into practical engineering marvels. They store energy in their spinning mass, ready to smooth out fluctuations or deliver power when needed. The stored energy grows with both inertia and the square of angular velocity, so designers often push for high rim speeds. But here physics raises a caution flag. Stresses inside the material rise in proportion to the square of velocity. Spin too fast and the wheel risks bursting apart from centrifugal tension. Engineers must strike a balance between maximum energy density and structural safety. Modern composites allow rim speeds unthinkable in iron or steel, but the principle remains. Energy storage grows quickly with speed, yet so do the stresses straining to tear the wheel apart. Angular momentum is the steadfast guardian of spinning systems. It is defined as the product of moment of inertia and angular velocity. L equals I times omega. What makes it fascinating is that if no external torque acts, the total angular momentum must remain constant. Change one part and the other must respond. This is why a figure skater pulling in their arm spins faster. The moment of inertia decreases, so angular velocity increases to keep L unchanged. The same principle explains why collapsing stars spin up into pulsars. The shrinking radius slashes inertia, and the remnant whirls at dizzying speeds to preserve angular momentum. When a torque is applied at right angles to angular momentum, something counterintuitive happens. The object does not tip in the direction of the push, but precesses, slowly rotating its spin axis around. The rate of this precession is equal to torque divided by angular momentum, written as omega equals tau divided by L. The larger the spin angular momentum, the more stubborn the gyroscope is against tilting. A fast-spinning wheel resists falling, even though gravity tugs on it, tracing a steady circular wobble instead. This is why gyroscopes, once set spinning, seem to defy intuition, holding themselves upright on thin supports that should not be able to balance them. That same principle underlies gyro compasses, which sailors and pilots prize for finding true north. Unlike magnetic compasses, which follow local magnetic fields, a gyro compass relies on Earth's rotation. A spinning gyroscope mounted in clever gimbals naturally aligns with the meridian, seeking the axis of Earth's spin. Over time, damping mechanisms bleed away oscillations until the device points stably north. This remarkable tool was crucial for navigation long before satellites and global positioning systems. giving ships and submarines a reliable sense of orientation even in regions where magnets were unreliable. In the weightless quiet of space, conservation of angular momentum finds a new stage. Satellites and spacecraft carry no giant rudders, yet they can change orientation with precision. They use reaction wheels, flywheels spun up or down by electric motors. When the wheel accelerates one way, the spacecraft body rotates the other way, conserving total angular momentum. This allows fine pointing for cameras, antennas, or scientific instruments without expelling fuel. Only when the wheels reach their maximum speeds do thrusters step in to reset them, a clever dance of conservation laws keeping billion-dollar instruments steady on distant worlds. Not all axes of rotation are created equal. A rigid body has 3 principal axes, each with its own moment of inertia. Spin about the axis with the largest or smallest inertia and motion is stable, but rotate around the intermediate axis and chaos looms. This is the intermediate axis theorem, sometimes called the tennis racket theorem. Toss a tennis racket into the air spinning about its handle, and it flips unpredictably. The same happens with a book spinning about its middle thickness. The mathematics shows that tiny deviations grow instead of shrinking, making this axis fundamentally unstable. It is a sobering reminder that even simple objects carry hidden quirks in their geometry. Even in the absence of torque, the motion of a spinning body can be richer than expected. Poinsot's construction shows that torque-free rotation of an asymmetric body traces out graceful but complicated paths. The angular momentum vector remains fixed in space, but the body itself seems to dance around it, as if rolling without slipping on an invisible cone. This leads to wobbling and nutation, motions familiar to anyone who has spun an oddly shaped object like a phone or a book. What looks like disorder is in fact the geometry of inertia making itself visible, a silent choreography dictated by the balance of mass within the object. Gravitational potential is one of those ideas that seems abstract at first, but proves to be enormously practical. Near a point mass, it takes the simple form minus g times m divided by r, where g is the gravitational constant, m is the mass creating the field, and r is the distance from its center. The minus sign reflects that gravity is attractive. You must do positive work to move a mass out to infinity, the chosen place where potential is defined as 0. What matters, though, are not the absolute numbers but the differences in potential. Moving a satellite from one orbit to another requires work equal to the change in potential energy, regardless of what arbitrary level you assign as 0. It is this focus on differences that lets engineers and astronomers compute orbital energies with elegant simplicity. Kepler's third law ties time and space together in a way that feels almost magical. For 2 bodies bound by gravity, the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. In words, t squared is proportional to a cubed. A planet twice as far from the Sun as Earth will take more than twice the time to orbit. It will take roughly 2.8 times longer. This law, derived centuries ago from painstaking observations of Mars, was later explained by Newton's theory of gravity and still forms the backbone of orbital mechanics. From moons around Jupiter to artificial satellites around Earth, the same relationship whispers its truth. The farther out you go, the slower the cosmic dance becomes. Not all orbits are perfect circles, and eccentricity is the measure of that stretch. At 0 eccentricity, the orbit is a circle. As eccentricity increases, the orbit elongates into an ellipse. This shape dictates speed variation. A body moves fastest at periapsis, the closest point to the central mass, and slowest at apoapsis, the farthest point away. Energy and angular momentum conspire to enforce this rhythm, and the change in speed can be dramatic. Earth's orbit is almost circular, so the variation is mild, but comets with high eccentricities race near the Sun and crawl at the edges of the solar system. The eccentricity, a single number between 0 and 1, captures whether a world strolls, jogs, or sprints through its year. Changing orbits efficiently is an art, and the Hohmann transfer is the classic maneuver. It uses two engine burns to move between two circular orbits in the same plane with the least possible change in velocity. First, a burn stretches the orbit into an ellipse that touches the target orbit. Then, a second burn at the other end circularizes it. Though simple, this strategy is energy efficient and underlies countless real missions. It is why sending a probe from low Earth orbit to a higher geostationary orbit involves two precise nudges rather than a brute force climb. The Hohmann transfer illustrates that in space travel, patience and geometry beat sheer muscle. Between two large bodies like Earth and the Sun, there exist special balancing points where gravity and orbital motion can cancel out in just the right way. These are the 5 Lagrange points. L1 sits between the bodies, L2 lies just beyond Earth, and L3 is opposite the Sun from Earth. More interesting are L4 and L5, which form equilateral triangles with the two bodies and are actually stable. Small objects placed there tend to stay put, drifting gently around those regions. In our own solar system, swarms of asteroids called Trojans occupy Jupiter's L4 and L5 points, moving in lockstep with the giant planet as it circles the Sun. These points are not science fiction conveniences but real and useful spots in the cosmic landscape. Get too close, however, and gravity can be destructive. The Roche limit marks the distance within which a fluid body held together only by its own gravity will be pulled apart by the tidal forces of a larger neighbour. If a moon ventures inside this limit around a planet, the difference in gravitational pull between its near and far sides can overwhelm its self-gravity, tearing it into a ring of debris. Saturn's magnificent rings are thought to be the remnants of such a disrupted body. The Roche limit is a stark reminder that gravity both builds and breaks, sculpting not only orbits, but also the fates of the worlds that wander too near. When a spacecraft performs a gravitational assist, it may look as though it has stolen free energy from a planet, but what is really happening is an exchange of momentum. As the spacecraft swings past, the planet pulls on it, and the spacecraft pulls equally on the planet. Because the planet is so massive, the change in its motion is imperceptible, but momentum and energy are conserved in the combined system. The result is that the spacecraft departs with a different speed and direction relative to the Sun, effectively borrowing a tiny fraction of the planet's vast orbital momentum. This trick has been used by missions like Voyager and Cassini to reach distant worlds without requiring impossible amounts of fuel, a celestial version of hitchhiking with planets as passing trucks. Low orbits are never truly permanent because Earth is wrapped in a thin atmosphere that stretches higher than most people imagine. Even hundreds of kilometers above the surface, there are still enough air molecules to matter. Each encounter saps a bit of the satellite's kinetic energy, causing its orbit to shrink. Interestingly, this drag tends to circularize the path as well. The low point of the orbit experiences the strongest braking, and over time the orbit smooths out before decaying completely. This is why the International Space Station, circling at about 400 kilometers altitude, requires regular reboosts to counteract drag and maintain its path. Without them, it would spiral down within a few months. Changing the tilt of an orbit relative to Earth's equator, known as inclination, is one of the most fuel-hungry maneuvers in orbital mechanics. A plane change means altering the spacecraft's velocity vector sideways, and the cost in delta V is proportional to the current speed. In low Earth orbit, where speeds are about 7.5 kilometers per second, even a 10-degree inclination change demands a huge burn. For this reason, Spacecraft are usually launched from locations that give them the desired inclination right from the start, using the rotation of Earth as free help. Once in space, engineers avoid large plane changes unless absolutely necessary, as they are some of the most expensive adjustments you can make. When tracking spacecraft around a planet, astronomers often use the concept of a sphere of influence. This is the region where the gravity of the smaller body, like Earth or Mars, dominates over the pull of the Sun for practical calculations of orbits. Inside this sphere, it makes sense to treat the spacecraft as orbiting the planet. Outside it, the Sun is the dominant master. The boundaries are not hard walls but smooth transitions. Yet the sphere of influence is invaluable for mission planning. It lets navigators switch between planetary-centered and sun-centered perspectives cleanly, as if the universe politely hands you a different map depending on where you are. Over long stretches of time, tidal forces can twist the fates of worlds. Tidal lock-in occurs when one body always shows the same face to another, like our moon forever turning one side to Earth. The time scale for locking depends sharply on distance and the body's internal structure. Closer orbits feel stronger tidal forces, pulling them into synchronization faster. Softer bodies with weaker rigidity deform more easily, bleeding energy and accelerating the process. This is why many moons in the solar system are tidally locked, while distant ones can still spin freely. Over geological ages, tides patiently tug until rotation and revolution fall into step. The gravitational pulls of multiple bodies also stir subtler, slower changes in orbits, known as secular perturbations. These are gradual drifts in the orientation of an orbit rather than abrupt shifts. The line of apsides, which connects the closest and farthest points of the orbit, can rotate slowly, changing where periapsis and apoapsis occur. Likewise, the line of nodes, where an orbit crosses a reference plane, can precess around over centuries. Earth's own orbit undergoes such shifts, contributing to long-term climate cycles known as Milankovitch cycles. Though invisible on human timescales, these quiet tugs accumulate, demonstrating that orbits are never perfectly fixed but evolve under the collective whisper of many gravities. A simple pendulum swinging back and forth feels like one of nature's most honest clocks, and under small angles it really is. The surprising detail is that the period of the swing, the time for one complete to and fro, does not depend on how heavy the bob is, nor on how wide the swing is, provided the angle remains small. The formula is period equals 2 pi times the square root of length divided by g, where g is the acceleration due to gravity. A heavy lead weight and a light wooden ball of the same string length keep time together, and even a child's gentle nudge or a sharper push produces the same beat if the angles are modest. Galileo famously noticed this in cathedral lamps swaying with equal rhythm despite differences in their size and swing. Only when the swings grow large does the independence break down and the pendulum reveals its limitations. Real oscillators do not keep going forever. Energy leaks away to their surroundings, whether through air resistance, internal friction, or some other channel. The motion decays in a way captured by an exponential. Amplitude shrinks like e to the power of minus bt divided by 2m, where b is the damping constant and m is the mass. The sharper the damping, the quicker the oscillation fades. To measure how clean the resonance is, physicists use the quality factor, or Q. A high Q oscillator rings for a long time, like a crystal goblet after being struck. A low Q oscillator, like a lump of clay, dies out almost immediately. Musical instruments, suspension systems, and even atomic clocks all rely on carefully tuned damping to find the balance between persistence and stability. Add a regular push to an oscillator and something new appears, a phase lag between the driving force and the motion. At low frequencies, the system moves almost in step with the push, At high frequencies, it lags far behind. Exactly at resonance, when the driving frequency matches the natural frequency, the lag is 90 degrees. The force is maximum when the displacement is 0. This is why children pumping a swing need to time their kicks just right. Too early or too late and the motion resists them, but perfectly timed and the swing soars higher. Resonance is both a blessing, amplifying useful vibrations, and a danger, as bridges and buildings have learned when winds or footsteps drive them at just the wrong rhythm. Oscillations can also grow when system parameters are varied rhythmically rather than forces applied directly. This is parametric resonance, a phenomenon most easily pictured in a child pumping a swing by standing and squatting at the right moments instead of kicking. Here the person is modulating the effective length of the pendulum, and energy sneaks in with every cycle. In mathematics, the governing equations gain a time-dependent parameter, and under certain conditions the oscillation amplitude increases dramatically. Engineers encounter parametric resonance in rotor shafts, power lines, and even electronic circuits, where changing a property in sync with the motion can create unexpectedly large responses. Of course, nature rarely offers perfect springs or flawless pendulums. Real oscillators often show enharmonicity. Their period shifts subtly with amplitude. Pull a spring far beyond its comfort zone and Hooke's law, force proportional to displacement, begins to falter. The restoring force grows weaker or stronger than expected, and the result is that larger oscillations take either longer or shorter than small ones. This departure from the simple harmonic world is what gives rise to richer overtones in music, complex dynamics in molecular vibrations, and practical limits on mechanical systems. In an ideal textbook spring, every oscillation is identical. In reality, the wider you swing it, the more the clock starts to drift. When two oscillators are coupled, a completely new behavior emerges. Imagine two pendulums connected by a weak spring. Start one swinging, and gradually it slows as energy slips across to the other, which begins to swing in sympathy. The exchange continues back and forth in a graceful dance, with both oscillators taking turns holding the energy. These systems can be analysed in terms of normal modes, patterns where both oscillators move together at fixed relative amplitudes and frequencies. Coupled oscillators lie at the heart of everything, from molecules vibrating in unison to power grids keeping phase. What begins as a simple back and forth becomes, when linked, a collective rhythm greater than the sum of its parts. The wave equation is one of physics' most elegant tools, and its solutions are as simple as they are powerful. It tells us that a disturbance, whether a ripple on water, a sound in air, or a pulse on a string, can travel indefinitely at a constant speed without changing its shape. Imagine flicking one end of a taut rope. The pulse that runs along it is a direct expression of the wave equation, moving forward cleanly at speed v. Unlike a thrown ball which slows and drops, the mathematical form of the wave equation guarantees that the ripple keeps its identity while it travels. It's why we can hear voices across a room or see sunlight from millions of kilometers away. The equation allows information and energy to move predictably from one place to another. When waves are confined, the story becomes even richer. Place them between boundaries, like the ends of a violin string or the walls of an organ pipe, and only certain wavelengths fit neatly. These boundary conditions quantize the allowed patterns. On a string fixed at both ends, the wave must have nodes at each end, which means only half wavelengths that fit into the string's length are permitted. This restriction creates harmonics, the set of frequencies we recognize as musical notes. In pipes, the same principle gives rise to standing sound waves that make instruments sing. Instead of a continuum of possibilities, the wave is forced into a discrete set of modes, each one a natural resonance of the system. Not all waves travel at the same speed. even in the same medium. Dispersion occurs when the velocity of a wave depends on its frequency or wavelength. Imagine dropping a stone into a lake. The ripples of different sizes spread at slightly different speeds, reshaping the packet of waves as it moves outward. Depending on whether velocity increases or decreases with frequency, the sign of dv over dk, the derivative of velocity with respect to wave number, the wave packet can flatten out or sharpen. In optics, this is what separates white light into rainbows as different colours spread apart inside a prism. In ocean swells, it means the larger, slower waves can lag behind or race ahead, giving seas their shifting character. Dispersion ensures that wave packets are rarely simple, but always dynamic. Sometimes, though, the medium refuses to play nice. In certain conditions, the speed of a wave depends not just on frequency, but also on amplitude. When larger disturbances move faster than smaller ones, the wavefront can catch up with itself, piling up until it forms a shock. This is the physics behind sonic booms. As an aircraft approaches the speed of sound, pressure waves compress into a steep front that releases with a bang. In fluids, shock waves appear as sharp jumps in pressure, density, and temperature. Nonlinearity here breaks the smoothness of ordinary waves and creates sudden boundaries that carry enormous energy. Shocks remind us that while the wave equation often predicts gentle undulations, reality sometimes delivers abrupt walls of force. Remarkably, waves can also find a balance between distortion and dispersion, creating solitons, self-preserving pulses that travel long distances without changing shape. First noticed in the 1800s when a solitary wave rolled down a canal without dissipating. Solitons occur when the spreading effect of dispersion is exactly countered by non-linear steepening. They pop up in water, optical fibers, and even plasma physics, stubbornly maintaining their form where ordinary waves would smear out or collapse. Solitons are a striking example of how nature finds equilibrium in unlikely places, building structures of stability from forces that normally undo one another. One final distinction completes the picture. Energy and information in a wave travel with the group velocity, while the crests and troughs themselves may race ahead at the phase velocity. In some media, the phase velocity can even exceed the speed of light, but this does not break relativity because no signal or energy outruns the group velocity. It is a little like watching shadows on a wall. The point where the shadow moves can sweep faster than any physical object, but no actual information has leapt ahead. In waves, the true courier of influence is the group velocity, steady and bound by the fundamental speed limits of the universe. In air, sound travels by tiny compressions and rarefactions passing from molecule to molecule, so warmer air, where molecules move faster, passes the pressure pulse along more quickly. The speed in a gas scales with the square root of absolute temperature. In words, speed equals the square root of gamma times k sub b times temperature divided by molecular mass, or equivalently the square root of gamma times pressure over density. That is why sound travels faster on a hot summer day than on a frosty morning. In solids, the story shifts. Stiffness dominates. A rigid solid resists deformation, so the restoring force is strong and the sound speed rises with elastic modulus. In words, speed equals the square root of elastic modulus divided by density. Steel, with high stiffness, carries sound much faster than rubber, and wood beats air by a wide margin, which is why you can sometimes hear a distant train through the rails before you hear it in the air. Human speech owes much of its richness to formants, the resonant frequencies of the vocal tract. Your lungs provide airflow, the vocal folds create a buzz rich in harmonics, and then the mouth, tongue, and lips shape this buzz into vowels by tuning the cavities. Each vowel corresponds to a particular set of formant frequencies. Usually the first two are most important. So E, ah, and are like different rooms that prefer different notes. Move the tongue forward and the first formant frequency falls while the second rises. Round the lips and both can shift downward. Singers and voice coaches learn to steer formants to project clearly, and speech recognition systems map these spectral peaks to classify sounds. Formants are why a whisper, even without vocal fold vibration, still carries recognizable vowels. The resonances remain. Sometimes architecture becomes an instrument. Whispering gallery modes occur when curved walls guide sound around a circular path, letting a murmur at one focus arrive audibly far away. In grand domes and circular corridors, waves hug the boundary, repeatedly reflecting at shallow angles, so little energy leaks into the interior. The result feels like a secret passage for sound. Historic sites like St. Paul's Cathedral in London famously demonstrate this effect, and similar physics appears in optics where light skims along curved microcavities. The key is geometry. The right curvature traps certain wavelengths in circulating paths, turning a hallway into a high-quality resonator. Whenever a sound wave meets a boundary between two materials, part of it transmits and part reflects, and the split depends on acoustic impedance, the product of density and sound speed. A large impedance mismatch, such as air against water, sends most of the energy back. This is why yelling underwater sounds faint from above, and why a stethoscope's soft diaphragm improves coupling between air and skin. To reduce reflections, engineers use matching layers whose impedance sits between the two media, smoothing the transition the way a good on-ramp eases traffic onto a motorway. Concert halls exploit these principles too, scattering sound with panels to avoid harsh echoes while preserving clarity. Active noise control takes a more cunning route. It generates an anti-sound that is equal in amplitude and opposite in phase to the unwanted noise. Superposition does the rest. If the offending pressure wave peaks, the anti-wave dips by the same amount and the sum cancels. The trick is timing and localization. Headphones put microphones and speakers close to your ears, measure the incoming noise, and produce the inverted signal within milliseconds. This works best for steady, predictable sounds like engine hums and air conditioner rumbles. For chaotic, high-frequency chatter, cancellation is harder because phase must be matched precisely, and the required anti-sound varies from point to point. Ultrasound imaging turns echoes into pictures. A handheld probe emits short bursts of high-frequency sound, typically in the range of a few megahertz, then listens for reflections. By measuring the time of flight, the device computes depth in words. Distance equals speed of sound multiplied by time divided by 2, with the division by 2 accounting for the out and back journey. Different tissues scatter and reflect differently, because their acoustic impedances vary, producing contrast that reveals boundaries, organs, and moving blood. Techniques like Doppler ultrasound add speed information by detecting tiny frequency shifts from flowing fluid. All of this happens without ionizing radiation, making ultrasound a safe, real-time window into the body powered by the gentle physics of echoes. Pascal's law is a beautifully simple rule that underpins everything from car brakes to hydraulic lifts. It states that a change in pressure applied to a confined fluid is transmitted equally and undiminished in all directions. Push on the fluid at one spot, and every part of the container feels it. This is why a small force applied on a narrow piston can lift a car if that piston is connected through fluid to a larger piston. The pressure is the same on both, but the larger area multiplies the force. In words, force divided by area is equal to pressure, so equal pressure across unequal areas creates unequal forces. It is a law that takes the invisible jostling of molecules and turns it into everyday power tools. The hydrostatic paradox is another gem of fluid thinking. Imagine 3 containers of different shapes but all filled to the same height with liquid. Even though one container might bulge outward, another taper inward, and the third stand straight like a cylinder. The pressure at the base is identical for all 3. It depends only on depth, density, and gravity. Expressed as pressure equals density multiplied by g multiplied by height. The total force on the base is simply this pressure times the base area. It does not matter if the container flares outward or narrows above. The weight of the liquid distributed along the sides balances the forces so that the bottom only feels the height. This paradox was striking to early scientists who assumed shape should matter. Fluids revealed that height rules all. In moving fluids, conservation of mass appears as the continuity equation. For incompressible, steady flow, the volume rate in must equal the volume rate out. In practical words, cross-sectional area multiplied by velocity is constant. A 1 square meter pipe carrying water at 2 meters per second feeds into a half square meter pipe, and the velocity doubles to 4 meters per second. This is why garden hoses speed up water when you press a finger against the opening. The smaller area forces the fluid to accelerate. Continuity is the simplest principle, but it governs everything from the narrow jets in fountains to the flow of blood through arteries. Bernoulli's principle adds energy into the picture, stating that along a streamline, pressure, kinetic energy per volume, and potential energy per volume add up to a constant. In the perfect world of frictionless flow, this total never changes. But in real pipes, viscosity steals energy. As fluid rubs against walls and layers shear over one another, energy dissipates as heat, so Bernoulli's constant falls as you move downstream. That is why pressure gradually drops along long pipes, and why pumps are needed to keep water moving in city networks. The principle remains a guiding light, but viscosity ensures that in practice, the numbers always slip lower. When a fluid meets a blunt object, another phenomenon emerges: flow separation. As the fluid wraps around the body, at some point it can no longer follow the curve, especially if the surface angle is sharp or the flow slows down. The fluid peels away, leaving a wake of low pressure behind the object. This low pressure zone drags back on the body, creating pressure drag far greater than skin friction alone. For spheres, cars, and airplanes, flow separation is the reason streamline shapes matter so much. A teardrop shape encourages the fluid to rejoin smoothly at the back, shrinking the wake and reducing drag. A flat-backed shape leaves a gaping vacuum region that resists forward motion. Under certain conditions, separation does not just leave a static wake, but produces a repeating pattern known as a Kármán vortex street. When a cylinder stands in a moving stream, alternating vortices shed from its sides, creating a beautiful zigzag trail of swirling eddies. The frequency of shedding depends on the Reynolds number, a ratio comparing inertial to viscous forces. These vortex streets can be mesmerizing to watch in water channels, but they also have practical consequences. The alternating forces can shake bridges, poles, or chimneys at regular intervals, sometimes causing dangerous vibrations. Designers often add helical strakes or aerodynamic modifications to break up the pattern, calming the flow so the structure does not hum or wobble itself to pieces. When a fluid flows past a solid surface, the very first layers of fluid behave differently than the free stream above them. Right at the surface, the fluid is forced to stick, creating a velocity of 0 at the wall. As you move away from the surface, the velocity gradually increases until it matches the free-flowing value. This thin region of changing speed is called the boundary layer. At low speeds or over short distances, the boundary layer remains laminar. Smooth, orderly sheets of flow slide past one another like pages of a book. But as velocity or length increases, disturbances amplify and the laminar order collapses into turbulence. The transition point depends on a dimensionless number called Reynolds number, which compares inertial to viscous forces. Below a certain threshold, laminar flow is stable. Above it, turbulence reigns. This shift matters greatly, because turbulent boundary layers mix more, carry more momentum, and alter drag characteristics. The skin friction drag on a flat plate behaves very differently, depending on whether the boundary layer is laminar or turbulent. In a turbulent regime, the friction coefficient scales roughly with the inverse square root of Reynolds number. In words, as Reynolds number grows, skin friction decreases, but only slowly. This means that at very high speeds, skin friction does not vanish. It remains significant, but it grows more gently than one might expect. Engineers studying aircraft wings, ship hulls, or pipelines must take this scaling into account, because at high Reynolds numbers, the frictional losses across enormous surfaces can become a major part of the total resistance. When it comes to reducing drag, the shape of the body matters more than the texture of the surface. A perfectly smooth but blunt body creates a large wake behind it, generating pressure drag that dwarfs skin friction. Streamlining a body, tapering its rear so the flow reattaches smoothly, shrinks this wake dramatically. That is why airplanes have sleek fuselages and why fish evolved tapered bodies. Streamlining sacrifices a little surface area, which might increase skin friction slightly, but the payoff is a massive reduction in pressure drag. In practice, this is the key to efficient movement through fluids, not polishing endlessly, but shaping wisely. The generation of lift has its own elegant rule. According to the Kutta-Joukowski theorem, the lift per unit length of a wing is equal to circulation multiplied by density multiplied by free stream speed. Circulation here means the net rotation of flow around the wing, which emerges naturally when air flows faster over one surface than the other. The theorem captures the essence of lift without resorting to popular half-truths about air travelling farther. It simply says that if circulation exists, lift exists. Birds, insects and airplanes all exploit this principle, adjusting wing angles, shapes and even flapping patterns to manipulate circulation and generate the upward force that keeps them aloft. At high angles of attack, however, even the best wing can lose its magic. Stall occurs when the boundary layer can no longer cling to the surface and separates prematurely. Instead of flowing smoothly to the trailing edge, the air peels away, leaving a turbulent, chaotic wake on top. Lift drops sharply, drag spikes, and control can be lost. Pilots feel this as a sudden mushiness in the controls or a buffet of shaking air. The phenomenon is not a failure of the wing itself, but of the flow around it. Modern aircraft often carry devices like slats and vortex generators to delay stall, but the underlying physics remains a delicate dance between flow attachment and separation. One of the stranger quirks of drag is something called the drag crisis. For a smooth sphere or cylinder, the drag coefficient does not simply rise or fall smoothly with Reynolds number. Instead, as the flow transitions from laminar to turbulent, there is a sudden drop in drag. This happens because a turbulent boundary layer clings to the surface longer before separating, reducing the size of the wake. Golf balls famously exploit this with their dimples. The roughened surface triggers early turbulence, shrinking the wake and letting the ball fly farther. The drag crisis is a vivid reminder that turbulence is not always a nuisance. It can sometimes be harnessed to reduce resistance and improve performance. Temperature feels intuitive, hot coffee versus cold ice, but in thermodynamics it takes on a precise meaning through the Zeroth law. It says that if system A is in thermal equilibrium with system B, and B is in equilibrium with system C, then A and C must also be in equilibrium with each other. This simple-sounding rule allows us to define temperature consistently. Without it, thermometers would be useless. A mercury bulb could be in balance with your skin, and your skin with the air, yet the bulb and air might not agree. The zeroth law ensures they do, and so temperature becomes the universal label of thermal sameness. It is called zeroth because scientists realized, after stating the first and second laws, that this more fundamental idea had to come before them. To measure heat directly, we turn to calorimetry, which translates energy into observable temperature changes. Place a hot object into cooler water, and the water's temperature rise reveals how much energy the object surrendered, assuming no losses. The key principle is conservation of energy. Heat lost equals heat gained. Calorimeters can also measure latent heats, where temperature does not change at all, but energy flows to melt ice or vaporize water. In these cases, the thermometer flatlines until the phase change completes, a subtle reminder that heat is not the same as temperature. From chemistry classrooms to bomb calorimeters measuring fuel content, this method has been the practical way of making heat visible and countable. Thermodynamics also distinguishes between functions that depend only on the current state and those that depend on the path taken. Internal energy, enthalpy, entropy, and Gibbs free energy are state functions. They are fixed once you know the pressure, temperature, and composition, no matter how you got there. Heat and work, by contrast, are path-dependent. Compressing a gas quickly or slowly deposits different amounts of heat in the surroundings, though the final internal energy may be identical. State functions provide the steady landmarks of thermodynamics, letting scientists compute energy balances without rehashing every detail of the journey. Equations of state tie together the fundamental quantities of pressure, volume, and temperature. The most famous is the ideal gas law. Pressure multiplied by volume equals the number of moles times the gas constant times temperature. In symbols, PV equals nRT. It describes gases as perfectly elastic billiard balls bouncing in a container, ignoring their size and ignoring any attractions between them. This approximation works remarkably well for many conditions and forms the backbone of chemistry and physics calculations, from predicting how much air fits in a tire to calculating the lift of a hot air balloon. Real gases, however, are less polite. Molecules have finite sizes that eat into available volume, and they attract one another, reducing pressure compared with the ideal prediction. Johannes van der Waals modified the ideal gas law to account for these effects. His equation adds a correction for volume, subtracting the space occupied by molecules themselves, and a correction for pressure, which includes the attractions. With these tweaks, the model explains why gases condense into liquids, why carbon dioxide can be bottled under pressure, and why ideal assumptions falter near critical points. It is a lesson in humility. Nature rarely offers perfection, but it often offers patterns close enough to be useful until you look very closely. Finally, thermodynamics measures how a substance's volume responds to changes in pressure and temperature with two key quantities: compressibility and expansivity. The isothermal compressibility tells you how much the volume shrinks when pressure rises while temperature is held constant, and the thermal expansivity tells you how much the volume grows when temperature rises while pressure is held fixed. Water, for example, is famously resistant to compression, which is why hydraulic systems work so well, yet it expands anomalously as it cools near 4 degrees Celsius, which is why ice floats. These coefficients reveal not just engineering properties, but also hidden quirks of matter, connecting macroscopic behavior to molecular structure. The first law of thermodynamics is the grand bookkeeper of energy. It says that the change in the internal energy of a system equals the heat added minus the work done by the system. In words, delta U equals Q minus W. This law is nothing more than conservation of energy written for thermal systems, yet it is profound in its reach. Heat can become work, work can become heat, and energy can flow between system and surroundings, but the balance sheet always closes. If you compress a gas, you increase its internal energy partly by mechanical work, and if you heat it, the same change in internal energy can occur without moving a piston at all. The details may vary, but the accounting never wavers. Energy is neither created nor destroyed, only shuffled between forms. The second law adds a sobering restriction to this bookkeeping. It declares that no cyclic process can convert all heat into work. In practice, this means no engine is 100% efficient. Some energy must always spill into the environment as waste heat. Steam engines, combustion engines, and even modern turbines bow to this principle. The second law is also why heat flows spontaneously from hot to cold, never the other way around, unless extra work is done. It gives us the arrow of time. While the first law is impartial about direction, the second law insists that entropy, the measure of disorder, or the spreading of energy, must increase in isolated systems. Engines may strive for efficiency, but the second law is the quiet voice reminding us that there will always be losses. The third law places a boundary on this progression by anchoring entropy. It states that as temperature approaches absolute zero, the entropy of a perfect crystal approaches zero as well. This does not mean every system can actually reach absolute zero, but it gives us a reference point for measuring entropy absolutely, not just in differences. The closer you get to 0 kelvins, the harder it becomes to extract more energy or reduce disorder further, because the system's states become more and more frozen into place. This law explains why cooling becomes increasingly difficult the nearer you approach absolute zero. Each step down requires disproportionately more effort. It also underpins modern cryogenics and our understanding of low-temperature physics. The flow of particles is governed by chemical potential, a concept that acts like a pressure but for matter itself. Just as water runs downhill in pressure until balance is achieved, particles flow from regions of higher chemical potential to lower. 2 tanks of gas connected by a valve will equalize not only in pressure, but also in chemical potential, balancing temperature, pressure, and composition. In batteries, electrons move under a difference in electrochemical potential. In biological systems, ions move across membranes following chemical potential gradients, powering nerve signals and cellular pumps. It is the driving force that ensures matter seeks equilibrium just as heat does. The second law can also be stated through the Clausius inequality, which sets the rule for cycles. The integral of heat divided by temperature over any cycle is less than or equal to 0. This inequality formalizes the one-way direction of spontaneous processes. A refrigerator can pump heat from cold to hot, but only by doing external work. Left to itself, energy disperses, entropy rises, and cycles cannot loop with perfect balance. The Clausius inequality is the rigorous skeleton beneath the intuitive statement that heat flows downhill. It turns intuition into mathematics, sharpening the second law into a precise tool. Finally, engineers reach for the concept of exergy, the maximum useful work that can be extracted from a system relative to its environment. While energy is conserved absolutely, exergy measures how much of that energy can actually be harnessed for work. A tank of warm water contains energy, but if the environment is equally warm, there is no exergy. No useful work can be extracted because there is no difference to exploit. Drop the same water into a cold environment and suddenly work becomes possible as heat flows outward. Exergy highlights the value of gradients, not raw amounts, and serves as a measure of how far a system is from equilibrium with its surroundings. It is the practical compass that tells us not just what energy exists, but what energy is truly available. Materials differ astonishingly in their ability to conduct heat. Metals like copper and silver are superb conductors because their free electrons carry thermal energy quickly through the lattice, while wood and rubber barely conduct at all. Diamond is so effective a conductor that it outperforms even copper, thanks to the stiffness of its crystal lattice, which passes vibrations rapidly. On the other extreme, aerogels, those ethereal solids that look like frozen smoke, have such low conductivity that they act as extraordinary insulators. The range spans many orders of magnitude, from less than 0.01 watts per meter per Kelvin for aerogels to over 1,000 for diamond. This variability is why the choice of material makes or breaks designs in engineering, from frying pans that spread heat evenly to spacecraft that need to shield instruments from scorching sunlight. When a warm object cools in moving air or fluid, convection takes over. Newton's law of cooling models this process with a simple proportionality. The rate of heat loss is proportional to the temperature difference between the object and the surrounding fluid. In words, heat flux equals H times delta T, where H is the convective heat transfer coefficient. This coefficient depends on fluid speed, viscosity, and surface geometry. A hot mug of tea left on the counter loses heat slowly in still air, but much more quickly if you blow across it, because faster air means larger H. This same principle scales up to cooling towers, radiators, and even the sweating of skin, all of which exploit the convective transfer of heat carried away by flowing fluids. Radiation adds yet another layer, because every surface emits electromagnetic waves according to its temperature. The power exchange between surfaces depends not only on temperature, but also on their emissivities, how good they are at emitting and absorbing, and the view factor, which quantifies how much of one surface sees another. Two parallel plates facing each other exchange far more radiation than two plates side by side simply because of geometry. Shiny, reflective surfaces like polished aluminum have low emissivity, so they radiate and absorb poorly, while matte black paint is nearly ideal. Engineers exploit these properties constantly, coating spacecraft in reflective foils or designing building materials that either trap or shed radiant heat depending on climate. In vacuum systems where convection and conduction vanish, radiation dominates, and engineers fight it with multi-layer insulation. This is the familiar silvery blanket wrapped around satellites. The principle is to stack many thin reflective layers separated by spacers, so each layer bounces away radiation while allowing very little heat to pass through. Even though each layer is only micrometers thick, together dozens of layers reduce heat flow dramatically. In the void of space, where there is nothing to convect heat away, such insulation is the difference between instruments overheating in sunlight or freezing in shadow. It is a practical shield against the most relentless mode of heat transfer. A more ingenious device is the heat pipe, which transports thermal energy efficiently using evaporation and condensation. Inside a sealed tube, a liquid evaporates at the hot end, carrying latent heat as vapor to the cooler end, where it condenses and releases that energy. Capillary action in a wick structure then draws the liquid back to the hot end, creating a continuous cycle without pumps or moving parts. The process exploits phase change, which moves much more energy per unit mass than simple conduction. Heat pipes are light, reliable, and astonishingly effective, used everywhere from laptop computers to satellites, quietly shuttling heat to where it can be managed. Even with excellent materials, heat transfer is not always smooth. At the microscopic level, surfaces are never perfectly flat, so when two solids touch, real contact occurs only at tiny points where asperities meet. The rest of the area is filled with air or other gaps, which are poor conductors. This introduces thermal contact resistance, a bottleneck that can dominate the overall heat flow, especially when the bulk materials themselves are good conductors. Engineers combat this with thermal greases, soft pads, or solder that fill the gaps, creating better pathways for heat. Without addressing this hidden resistance, the best copper block or aluminum plate can perform no better than wood at transferring heat across a joint. Statistical physics takes the unruly world of countless particles and tames it with averages. Instead of tracking every atom, it imagines ensembles, conceptual collections of possible microstates that satisfy certain constraints. The microcanonical ensemble assumes fixed energy, volume, and particle number, like a perfectly isolated box of gas. The canonical ensemble allows energy to fluctuate while temperature is fixed, as if the system shares heat with a reservoir. The grand canonical ensemble goes a step further, allowing both energy and particle number to vary, controlled by chemical potential. Each ensemble is a different lens, but remarkably, in the limit of many particles, they all converge to the same macroscopic predictions. This flexibility makes ensembles the language of choice for connecting microscopic chaos to macroscopic calm. At the heart of every ensemble sits the partition function, denoted Z, a deceptively simple sum that encodes nearly everything. For the canonical ensemble, Z equals the sum over all microstates of E to the power of negative energy over K times T. From this single object, you can extract free energy, entropy, internal energy, heat capacity, and fluctuations. In practice, the partition function is the machine that turns microscopic possibilities into macroscopic laws. Compute Z, and you have the key to predicting how a gas expands, how a magnet aligns, or how a crystal vibrates. It is a statistical Rosetta Stone translating probabilities into thermodynamics. Particles themselves divide into two grand families with distinct statistics. Fermi-Dirac statistics govern fermions, particles with half-integer spin like electrons, protons, and neutrons. They obey the Pauli exclusion principle, which forbids any two fermions from occupying the same state. This rule explains the rigid structure of atoms, the architecture of the periodic table, and the very stability of matter. Bose-Einstein statistics, by contrast, apply to bosons, particles with integer spin such as photons or helium-4 atoms. Bosons happily crowd into the same state, leading to phenomena like lasers and superfluidity. The difference between cannot share and must share shapes the entire universe, from the stiffness of matter under your feet to the coherence of light in a laser pointer. Near a critical temperature, matter displays a striking optical effect known as critical opalescence. As a liquid approaches its critical point, density fluctuations grow larger and longer in scale. Correlation lengths, the distances over which fluctuations are linked, become so vast that light scattering increases dramatically. A once clear fluid becomes milky, glowing as if infused with opal. This behavior is a direct signal of the microscopic order breaking down, with regions of high and low density constantly shifting across many scales. To the eye, it is beautiful. To physics, it is a visible manifestation of universality, the idea that diverse systems share the same behavior near criticality. Randomness and response are not separate worlds, and the fluctuation-dissipation theorem ties them together. It states that the way a system responds to a small external force is directly related to the natural fluctuations it exhibits at equilibrium. In other words, the noise you see in a system carries within it the fingerprint of how it will react if you poke it. This principle underlies everything from electrical resistance to Brownian motion of particles. The jiggle of pollen grains in water, studied by Robert Brown in the 1800s, is the same dance that reveals diffusion constants and viscosities. Noise is not a nuisance here, it is a window into the underlying laws. The Gibbs paradox once puzzled scientists when mixing two identical gases. If entropy is a measure of disorder, mixing two samples of the same gas should not increase entropy. After all, nothing has changed. Yet naive calculations suggested it did. The resolution comes from the indistinguishability of identical particles. When we account correctly for the fact that swapping two identical atoms does not create a new state, the paradox vanishes. Entropy increases only when mixing different species, not identical ones. This insight is one of the stepping stones that led to quantum statistics, where indistinguishability is not a philosophical choice but a fundamental truth of the microscopic world. Phase transitions are where matter reveals some of its most dramatic tricks, shifting from one form of order to another. A first-order transition is marked by a sudden jump and the absorption or release of latent heat. Melting ice is the textbook example. The temperature of the ice-water mix stays constant at 0 degrees Celsius, while energy flows in, not raising the temperature but breaking molecular bonds. Boiling water at 100 degrees Celsius behaves the same way. In these transitions, two phases can coexist while energy goes into changing the structure rather than raising the thermal motion. Second-order transitions, in contrast, have no latent heat. Instead, they are continuous changes, like the loss of magnetization in iron as it warms past its Curie temperature. Here the transition is smooth, but subtle features like heat capacity spike, showing that the system is reorganizing itself without a sharp break. A helpful way to keep track of such changes is through an order parameter, a measurable quantity that signals the degree of symmetry breaking across a transition. In a ferromagnet, the order parameter is magnetization, 0 above the Curie point, non-zero below it. In a liquid-gas transition, density difference between phases acts as the order parameter. These parameters capture the essence of before and after, condensing the complexity of microscopic arrangements into a single value. As temperature or pressure shifts, the order parameter maps the system's internal reorganization, showing whether the material is in one phase, another, or straddling the boundary. Despite the variety of physical systems, magnets, fluids, superconductors, many of them fall into universality classes when approaching critical points. These classes share the same critical exponents, which describe how quantities like correlation length, susceptibility, or order parameter scale near the transition. The microscopic details may differ wildly, but the large-scale behavior is the same. This universality is one of the deep triumphs of statistical physics. Whether you're boiling liquid carbon dioxide or studying a ferromagnetic crystal, the mathematics governing the critical behavior rhymes. The system forgets its details and displays a common pattern, as though all of nature has been reading from the same script. If a system is driven through a transition too quickly, it cannot keep up smoothly and defects form. This is the essence of the Kibble-Zarek mechanism. Imagine rapidly cooling a fluid through its critical point. Domains of the new phase emerge, but because the change was too fast, they cannot coordinate perfectly across the whole material. The mismatches leave behind defects, like vortices, dislocations, or domain walls, that persist. The mechanism was first proposed in cosmology to explain defects in the early universe after rapid cooling from the Big Bang, but it applies equally to lab systems like liquid crystals or superfluid helium. It connects the cosmos to the laboratory with a single principle: rush, a transition, and order comes with scars. Not all changes proceed by nucleation, where tiny seeds of the new phase grow. In some regions of the phase diagram, systems can undergo spinodal decomposition, where fluctuations spontaneously grow without needing a critical nucleus. Picture a supersaturated solution or a rapidly quenched alloy. Instead of waiting for a bubble or droplet to appear, the mixture instantly begins to separate into interwoven regions that coarsen over time. This pathway produces intricate patterns, labyrinths and mottled textures that slowly smooth out as domains merge. It is a fundamentally different route to phase separation, one where the barrier is gone and the system slides downhill into a new configuration. Ferromagnets and ferroelectrics display yet another fascinating behaviour: hysteresis. When an external field is cycled, the system's response does not simply retrace its path but lags behind, forming a loop on a graph of field versus order parameter. In magnets, the loop shows how magnetization persists even when the field is removed, only flipping after the field is reversed strongly enough. This memory effect is the basis of magnetic storage, but it also reveals that transitions can depend on history. The same system, under the same conditions, may be in different states depending on where it has been. Hysteresis loops are the footprints of path dependence, carved into the response of materials that remember their past. Coulomb's law is the starting point for understanding electric forces. It states that the force between two-point charges is proportional to the product of their charges, and inversely proportional to the square of the distance between them. In words, force equals 1 over 4 pi epsilon naught multiplied by q1 times q, 2 divided by r squared. Here epsilon naught, the permittivity of free space, sets the strength of the interaction in a vacuum. The 1 over r squared dependence means doubling the distance cuts the force to 1/4, and halving the distance increases it fourfold. This simple law echoes Newton's law of gravitation, but with the crucial difference that charges can be positive or negative, leading to both attraction and repulsion. It is this symmetry of push and pull that makes electric forces so versatile, shaping everything from atomic structure to lightning bolts. In electrostatics, electric potential provides a more intuitive way to think about fields. The potential at a point is the work required to bring a unit charge from infinity to that location. Importantly, the potential is path independent. No matter how you move the charge through the field, the work done is the same. This reflects the conservative nature of electrostatic forces. If you take a charge around a closed loop, the network is zero. Engineers exploit this property by assigning potentials to points in circuits, confident that the difference between two nodes tells the whole story, regardless of the route taken. It is what allows us to treat electrical networks with the same logic as hydraulic systems, with voltage acting as pressure. Capacitors show how electric fields themselves can store energy. Between two plates at different potentials, an electric field fills the space, and the energy per unit volume is 1/2 epsilon times E squared, where epsilon is the permittivity of the medium and E is the electric field strength. Unlike a spring which stores energy mechanically, a capacitor holds it in the invisible tension of the field. This is why capacitors can release bursts of energy so quickly. There's no inertia to overcome, only the collapse of the electric field as charges redistribute. Whether smoothing ripples in a power supply, timing the blink of a circuit, or delivering a flash in a camera, capacitors rely on this dense and rapid storage of electrical energy. On the magnetic side, the Biot-Savart law describes how currents generate magnetic fields. A tiny element of current contributes a small piece of magnetic field proportional to the current, the length of the element, and the sine of the angle, all divided by the square of the distance. Integrate these contributions over a wire, and you can predict the full magnetic field pattern. A straight wire produces concentric circles of magnetic field around it. A loop of current concentrates the field through its center, the basis of electromagnets. Though the formula may seem abstract, it is what links electricity to magnetism, showing that moving charges are the very source of magnetic fields. Magnetic materials respond to these fields in layered ways. The magnetic field intensity, called H, is the applied push produced by currents or external magnets. The magnetic flux density, called B, is the actual field inside the material, shaped by both the external field and the material's own response. Magnetization, called M, measures how strongly the material itself has aligned its microscopic magnetic moments. In simple linear materials, these quantities relate neatly. B equals mu naught times H plus M, or in many cases B equals mu times H, where mu is permeability. The dance between H, B and M explains why iron cores boost electromagnets so powerfully, why permanent magnets hold their strength, and why different substances respond so differently to the same applied field. Even magnetic fields themselves hold energy, just as electric fields do. The energy density stored in a magnetic field is 1/2 times B squared divided by mu, where mu is the permeability of the medium. This is the invisible reservoir that powers inductors, transformers, and magnetic resonance. In an inductor, energy builds in the growing magnetic field when current rises, only to be released back as current falls. Magnetic energy storage is less obvious to us than the stretched coil of a spring or the charged plates of a capacitor, but it is no less real. Entire machines hum because of it, and the whine of a transformer is, in part, the sound of this invisible energy being shuffled and reshaped inside steel and copper. Maxwell's equations are the grand unifiers of electricity and magnetism, distilling centuries of experiments into 4 compact statements that describe the invisible weave of fields across space and time. The first is Gauss's law for electricity, written as the divergence of E equals rho divided by epsilon naught. It tells us that electric charges are sources of electric fields. Positive charges push fields outward, negative charges pull them inward, and the strength depends on the density of charge. Imagine enclosing a charge in a soap bubble. The total electric flux through the bubble's surface equals the enclosed charge divided by epsilon naught. Whether the bubble is big, small, or lopsided does not matter. The law holds true, making it a cornerstone of electrostatics. The second is Gauss's law for magnetism, which states divergence of B equals 0. No matter how closely you look, magnetic field lines never begin or end. They always form closed loops. This reflects the fact that magnetic monopoles have never been observed in nature. Split a magnet in half, and you do not get an isolated north and an isolated south. Instead, you get 2 smaller dipoles. The symmetry of magnetic fields, with their endless loops, gives them a character distinct from electric fields. It is a profound clue about the deep structure of nature, and though physicists still dream of discovering monopoles, Maxwell's law assumes their absence. The third law is Faraday's law of induction, written as the curl of E equals minus the time derivative of B. In simpler words, a changing magnetic field creates a circulating electric field. This is the law that underpins electric generators. As coils of wire move through magnetic fields, the time-varying flux induces currents. It also explains transformers, induction cooktops, and even the simple fact that moving a magnet through a loop of wire produces a spark of electricity. Faraday's discovery showed that electricity and magnetism were not separate forces, but 2 faces of a deeper unity, linked through time and change. The fourth equation is Ampere's law with Maxwell's correction. written as the curl of B equals mu naught times J plus mu naught epsilon naught times the time derivative of E. The first term, mu naught times current density J, describes how steady currents generate magnetic fields, just as Ampere discovered, but Maxwell added the second term involving the changing electric field to make the equation self-consistent. This displacement current term was revolutionary, allowing the equations to describe not only static situations, but also dynamic ones where fields vary with time. It is this correction that makes the entire system capable of supporting electromagnetic waves. When Maxwell combined the four equations, the mathematics revealed something extraordinary. The coupled fields naturally produce waves that travel through space at a speed equal to 1 over the square root of mu naught times epsilon naught. Plugging in the measured values of permittivity and permeability gave the speed of light. This was a breathtaking revelation in the 1860s, that light itself was an electromagnetic wave. What had seemed like separate domains of optics and electricity collapsed into a single framework. Suddenly, the glow of a candle and the crackle of a spark were understood as the same phenomenon expressed at different frequencies. The energy carried by these waves is tracked by the Poynting vector, written as S equals 1 over mu naught times E cross B. It represents the directional flow of electromagnetic power per unit area. If you picture an electromagnetic wave with electric and magnetic fields oscillating at right angles, the Poynting vector points perpendicular to both, in the direction the wave propagates. In a radio antenna, the Poynting vector describes how energy radiates outward. In a solar panel, it describes how sunlight delivers power to be harvested. Though invisible to our eyes, the Poynting vector is the mathematical flashlight that shows where the energy of electromagnetic fields is actually going. Kirchhoff's current law is the circuit world expression of charge conservation. It says that the total current flowing into a node must equal the total current flowing out. No electrons pile up at a junction, and none vanish into thin air. What enters must leave. In a simple T-junction of wires, if 2 amperes flow in from the left and 3 amperes flow in from the right, then 5 amperes must flow out the bottom. This principle holds at every node. Whether it is a humble breadboard or a sprawling power grid, it ensures that circuits, no matter how tangled, obey the universal rule that charge cannot accumulate endlessly. Kirchhoff's voltage law is the partner rule, applying conservation of energy to electric loops. It states that the algebraic sum of all potential rises and drops around any closed loop is 0. Walk around a loop in a circuit diagram, adding the gains from batteries and subtracting the drops across resistors, capacitors, and other elements, and you must end where you began. This is why Ohm's law can be used reliably in circuits. The energy supplied by a source must equal the energy dissipated or stored in the elements it powers. Together with the current law, the voltage law provides a pair of balancing scales that can solve any network of resistors and sources. Complex circuits often look intimidating, but Thevenin's and Norton's theorems let you swap that complexity for simplicity. Thevenin's equivalent reduces a network to a single voltage source in series with a resistance, while Norton's equivalent reduces it to a current source in parallel with a resistance. These equivalents let engineers model a whole power supply, with all its hidden resistors and internal quirks, as one simple source plus one resistor. Switch between Thevenin and Norton with a straightforward conversion, and suddenly messy networks shrink into neat, solvable forms. This simplification is why entire textbooks lean on these theorems. They strip problems to their essence. Resistor-capacitor circuits bring time into play. Connect a resistor and capacitor in series and charge the capacitor through the resistor, and the voltage does not leap instantly but rises gradually, following an exponential curve. The timescale is set by tau equals R times C, called the time constant. After 1 tau, the capacitor reaches about 63% of its final voltage. After 5 taus, it is practically there. Discharging follows the same exponential law in reverse. This smooth timing behavior is the heartbeat of filters, timers and oscillators, giving electronics their ability to stretch, delay, and shape signals. Diodes break the symmetry of circuits by conducting electricity far more easily in one direction than the other. Their current-voltage relationship is exponential, not linear, and conduction begins only after a threshold voltage is exceeded. For silicon diodes, this is about 0.7 volts. Below that, current is tiny. Above it, current rises rapidly. This nonlinear nature makes diodes indispensable for rectifying alternating current, detecting radio signals, and protecting circuits from reverse polarity. Their effective resistance is not fixed but changes with the operating point, leading engineers to speak of dynamic resistance. These subtleties are what make diodes simultaneously simple to draw and endlessly rich in behavior. Transistors take the idea of directional control and elevate it into full amplification and switching. At heart, they act like controllable current sources. In a bipolar junction transistor, a small input current into the base allows a much larger current to flow between collector and emitter. In a field effect transistor, a voltage applied to the gate controls current between source and drain by shaping the channel's conductivity. These devices can switch in nanoseconds and scale up into billions on a single chip. They form logic gates, memory cells, and amplifiers, the literal foundation of modern computing. A transistor may be drawn as a tiny symbol, but it embodies one of the greatest revolutions in applied physics, turning the flow of electrons into the flow of information. In alternating current circuits, components resist the flow of energy in time-dependent ways, and this resistance is called reactance. A capacitor resists low-frequency signals more than high-frequency ones. Its reactance is given by 1 divided by omega times C, where omega is the angular frequency and C is the capacitance. At very low frequency, the capacitor behaves almost like an open switch, blocking current. At very high frequency, its reactance shrinks, and it acts almost like a short circuit. Inductors behave in the opposite manner. Their reactance equals omega times L, with L being inductance. At low frequencies, the inductor offers little resistance, but at high frequencies, the reactance grows and the inductor increasingly blocks the signal. This duality makes capacitors and inductors the yin and yang of alternating current design, complementary tools for shaping signals. To handle resistors, capacitors, and inductors together, engineers combine them using the language of impedance, a generalization of resistance to alternating current. Impedance is a complex number, written as R plus J times X, where R is resistance and X is reactance. Capacitors contribute negative imaginary reactance, inductors contribute positive imaginary reactance, and resistors stay purely real. By combining these as vectors on the complex plane, one can calculate not only how much current flows, but also how it lines up in phase with the voltage. This formalism makes messy time-dependent trigonometry manageable, reducing circuits filled with oscillating currents to neat algebra with complex numbers. Among the most elegant consequences of this interplay is resonance. In a circuit with an inductor and capacitor, the resonant angular frequency is equal to 1 divided by the square root of L times C. At this frequency, the inductive and capacitive reactances cancel perfectly, leaving only resistance to govern the circuit's behavior. Current can surge dramatically at resonance, producing sharp peaks in response. This principle underlies radio tuners. Turning the dial changes capacitance, adjusting the resonant frequency so that the circuit listens only to the chosen station. Resonance is also exploited in filters, oscillators, and countless devices that rely on sharp frequency selectivity. Reactance does not just affect amplitude, it also shifts phase. In capacitors, current leads voltage by 90 degrees. The capacitor happily accepts charge in advance of the voltage rise. In inductors, current lags, voltage by 90 degrees. The inductor resists changes in current, making the voltage lead. These phase relationships, though abstract at first, are crucial in alternating current design. They explain why circuits can draw current that does not contribute to useful power, and why power engineers obsess about alignment between current and voltage. In many ways, alternating current circuits are less about how much power flows and more about whether power and current are keeping time together. Transformers put all these principles to work in one of the most useful devices of modern civilization. By winding coils of wire around a magnetic core, transformers transfer energy from one circuit to another, raising or lowering voltage in the process. If the secondary winding has twice as many turns as the primary, the output voltage is doubled, while the current is halved. The total power, neglecting losses, remains the same. What is lost in current is gained in voltage, and vice versa. This near-constant power trade is what allows electricity to be transmitted across continents at high voltages with minimal losses, then safely step down to household levels. Without transformers, modern power grids simply would not exist. Finally, the subtlety of alternating current systems lies in reactive power, which circulates between sources and reactive components without doing useful work. A poor power factor, where current and voltage are out of phase, wastes capacity in power lines and transformers. Power factor correction, often achieved with carefully placed capacitors or inductors, realigns the phase so that current contributes more directly to real power. The benefit is efficiency, less energy lost in transmission, and smaller currents for the same delivered power. From industrial plants to your local utility, this quiet correction keeps the lights on with fewer wasted watts, ensuring that the grid hums smoothly rather than stumbling under reactive burden. Alternating current has a knack for being slippery to describe, because its voltage and current are always oscillating. To measure its heating power fairly against direct current, engineers use the root mean square or RMS value. This is the square root of the average of the square of the signal. For a pure sine wave, the RMS value of the voltage is equal to the peak voltage divided by the square root of 2. What this means in practice is that a 120 volt RMS household supply delivers the same heating effect as a steady 120 volt direct current source, even though the alternating current actually swings up and down between plus 170 volts and minus 170 volts. RMS values are what make alternating current comparable to direct current, translating a dance of waves into the language of steady heating. Once signals are represented in terms of frequency, filters become the sculptors of sound and data. A low-pass filter allows low frequencies through while blocking higher ones, taming sharp edges into smooth curves. A high-pass filter does the reverse, eliminating rumbling drifts while preserving crisp changes. Bandpass filters admit only a narrow slice of frequencies, acting like a tuning fork that resonates with just the right notes. Bandstop filters, their inverse, remove an unwanted frequency range, such as the pervasive 50 or 60 Hz hum of power lines. Whether inside radios, audio mixers, or wireless devices, filters are the sieves that sort signals by frequency, ensuring that only the desired parts pass while noise and clutter are reduced. When signals are digitized, another rule becomes critical: the Nyquist criterion. It says that to capture all the information in a signal without distortion, you must sample at least twice as fast as the highest frequency present. If you sample too slowly, aliasing occurs, where high-frequency details masquerade as low-frequency artifacts. Imagine taking snapshots of a spinning wheel. At the right frame rate, you see smooth motion, but if you sample too slowly, the wheel may appear to spin backwards or stand still. The same happens with digital sound and images. Compact discs, for instance, sample audio at 44,100 Hz, comfortably more than twice the upper range of human hearing, so that the music is preserved without aliasing. At very high frequencies, alternating current behaves differently in conductors due to the skin effect. Instead of flowing evenly through the wire's cross-section, the current crowds near the surface. The effective cross-sectional area shrinks, increasing the resistance compared to direct current. This effect grows with frequency, making it a serious consideration in radio frequency systems and power transmission. To mitigate it, engineers use stranded conductors with individually insulated strands, called Litz wire, or hollow tubes for radio transmitters, since the center of the conductor carries little current anyway. The skin effect is an invisible migration of electrons outward, but its consequences ripple across technologies that push into high-frequency domains. Signals sent along cables are not immune to subtle reflections either. Transmission lines behave like distributed systems, not just simple wires, and if the impedance of the line does not match the load, part of the signal bounces back. These reflections can cause standing waves, signal loss, and distortion. To avoid this, impedance matching ensures that the source, the line, and the load all share the same effective resistance. This is why coaxial cables are specified with values like 50 ohms or 75 ohms, and why antennas are carefully tuned. Impedance matching is like making sure a bridge and a road have the same width. Otherwise, traffic snarls at the transition. In modern electronics, efficiency is king, and switch-mode power supplies embody this pursuit. Unlike traditional linear supplies which burn off excess voltage as heat, switch-mode supplies chop the input power at high frequencies, often tens or hundreds of kilohertz, then transform and regulate it through inductors, capacitors, and semiconductors. The rapid switching allows for small, lightweight components and high efficiency, often exceeding 90%. These supplies power laptops, LED lighting, and phone chargers, delivering reliable output while wasting far less energy. They may whine faintly at their switching frequency, but they represent one of the quiet triumphs of applied physics, squeezing more useful work from every watt. Geometric optics begins with the simplest and most elegant of laws. The angle of incidence equals the angle of reflection. When a ray of light strikes a mirror, the incoming angle relative to the surface normal is identical to the outgoing one. This principle, discovered long before modern physics, underpins everything from shaving mirrors to periscopes. It is why flat mirrors faithfully reverse left and right but preserve angles, and why parabolic reflectors can focus parallel rays into a single point. The law is so consistent that engineers can design entire optical systems just by drawing straight lines and applying the symmetry, confident that light will obey. Lenses add complexity by bending light rather than bouncing it, and the lens maker's formula links their curvature, material, and focal length. In words, 1 divided by focal length equals the refractive index -1, multiplied by the sum of 1 over the radius of curvature of the first surface -1 over the radius of curvature of the second surface. By adjusting curvature or using glass with different refractive indices, opticians can craft lenses for eyeglasses, cameras, and microscopes. This formula distills the geometry of arcs into practical predictions. Whether the lens will converge rays to a point or spread them apart, and how strong its focusing power will be. It is the rule that lets a thin piece of glass correct nearsightedness or bring distant galaxies into focus. Depth of field, the range over which objects appear sharp, depends strongly on aperture size. A smaller aperture increases the depth of field, making both near and far objects come into focus, as in landscape photography. But closing the aperture too much invites diffraction, where light bends around the edges and spreads, softening the image. This trade-off explains why there is no perfect setting. Wide apertures give shallow focus and creamy backgrounds, while narrow apertures yield extended sharpness, but risk losing crispness from diffraction blur. Every photographer, consciously or not, is balancing geometry against wave physics each time they choose an f-stop. Some optical systems, however, are designed not just for focus but for measurement. Telecentric lenses are built so that magnification does not change with object distance. Normally, move an object closer or farther from a camera, and its apparent size shifts. In telecentric optics, only rays parallel to the optical axis are accepted, so the image scale remains fixed. This makes them indispensable in industrial inspection, where precise measurements are needed regardless of positioning. The price is complexity and cost, but the benefit is accuracy, turning light into a ruler that never lies. Of course, real lenses are not perfect. Aberrations creep in, distorting the image. Spherical aberration occurs when rays far from the center of a spherical lens focus at slightly different points than rays near the center, producing a blurred image. Coma appears off-axis, where point sources stretch into comet-like smears. These flaws arise from simple geometries used in lens making, which do not perfectly control the paths of all rays. Correcting them requires clever combinations of elements, special shapes like aspheres, or digital post-processing. Optical design is often a battle against these distortions, striving to coax glass into acting as if it were flawless. The flow of light through an optical system is also controlled by apertures and stops. An aperture stop limits the bundle of rays that pass through, determining brightness and depth of field. A field stop limits the extent of the object that can be imaged, defining the field of view. These simple discs of metal or plastic shape the behavior of entire optical systems, setting their reach and their clarity. In cameras, the adjustable iris aperture balances exposure, blur, and diffraction. In telescopes and microscopes, stops dictate how much of the world can be seen and how sharply. They are the traffic managers of optics, quietly restricting and directing light to make images possible. When two beams of light overlap, they do not simply add brightness the way two flashlights do. Instead, they interfere, producing fringes of bright and dark bands that reveal differences in their paths down to the scale of a single wavelength. A difference of half a wavelength means perfect cancellation, while a full wavelength difference means reinforcement. This sensitivity to minuscule path differences is why interference experiments like Young's double slit were so revolutionary. They showed that light behaves as a wave. Today, interference patterns are still used in precise metrology, capable of measuring distances and displacements on the scale of nanometers, a feat impossible by any ruler. Diffraction, the spreading of light when it encounters an obstacle or slit, is another hallmark of wave behavior. Pass a beam through a narrow slit, and instead of continuing in a sharp line, it fans outward. Counterintuitively, the narrower the slit, the wider the spread. This inverse relationship is a consequence of light bending at the edges and overlapping itself, with the wavefront reorganizing beyond the slit. It is why no optical system can resolve infinitely small details. Diffraction places a hard limit on resolution. Telescopes, microscopes, and even your eyes live under the rule of diffraction, which explains why aperture size is so critical in determining clarity. Polarization adds a new layer of structure to light. A polarizer is a material that selects only one orientation of the electric field oscillation, blocking the perpendicular one. Malus's law describes what happens when polarized light passes through a second polarizer set at an angle theta. The transmitted intensity equals the original intensity times the cosine squared of theta. At 0 degrees, all the light passes. At 90 degrees, none does. This principle underlies polarized sunglasses, which filter out glare reflected from horizontal surfaces, and liquid crystal displays, which modulate light by twisting polarization. With a simple mathematical law, light's hidden vector nature becomes something we can control and use. Certain crystals go even further, splitting a single beam into two. Birefringence occurs when a material has different refractive indices for different polarization directions. A crystal of calcite, for example, will divide light into an ordinary ray and an extraordinary ray, each travelling at a slightly different speed and emerging in different directions. This splitting produces double images and rainbow-like effects, but it also powers devices like wave plates, which control polarization states, and optical fibers that use birefringence to reduce distortion. What might seem a quirk of geometry becomes a powerful tool in the optical engineer's kit. Holography is a dazzling application of interference, storing not only the brightness of light but also its phase information. By recording the interference pattern between a reference beam and light scattered from an object, a hologram encodes the full three-dimensional wavefront. When illuminated correctly, it reconstructs the original light field, producing a striking 3D image that shifts as you move your head. Unlike photographs, which flatten perspective, holograms preserve depth and parallax. They are used not just for novelty stickers, but also for data storage, security, and advanced imaging systems. The secret is interference, capturing both the amplitude and the phase in one delicate pattern. All of these effects depend on coherence, the degree to which waves remain in step over time and space. The coherence length is the distance over which light maintains a predictable phase relationship. Lasers, with their narrow frequency spread, have coherence lengths that can be kilometers long, allowing crisp interference fringes. Ordinary light bulbs, by contrast, emit a jumble of frequencies and phases, with coherence lengths of only micrometers, making interference effects vanish quickly. This is why interference fringes are so vivid with lasers, but absent in everyday illumination. Coherence defines the boundary between light as a useful way for precision and light as the familiar glow of daily life. In relativity, the most faithful clock is the one carried by the object itself. Proper time is defined as the time measured in the object's rest frame, ticking away along its own world line. No matter how fast the object is moving relative to an observer, its own internal clock reads time normally. For a traveller, a wristwatch always ticks at the same steady pace. It is only when comparing clocks across different frames that discrepancies appear. Proper time is the invariant heartbeat of relativity, the measure that all observers agree upon, even if they disagree about how much time has passed in their own coordinates. To relate these differing perspectives, special relativity introduces the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus the square of the velocity divided by the speed of light squared minus v squared over c squared. This factor shows up everywhere. It stretches time, length, and energy as objects approach the speed of light. At everyday speeds, gamma is almost exactly 1, but at 99% of the speed of light, it grows to more than 7. Time dilation, length contraction, and the sharp increase in kinetic energy all flow from this single mathematical expression. The Lorentz factor is the lever by which velocity bends the scales of space and time. One of the most counterintuitive consequences is the relativity of simultaneity. Events that seem to occur at the same time in one frame may not be simultaneous in another. For space-like separated events, even the order can reverse depending on the observer's motion. Imagine two lightning bolts striking opposite ends of a moving train. To someone on the ground, they may appear simultaneous, but to a passenger on the train, one strike occurs first. This is not an illusion, but a feature of how space and time intertwine. Simultaneity is not absolute. It is stitched into the fabric of each observer's frame of reference. Early in the 20th century, people sometimes described objects moving at high speed as gaining relativistic mass. But this concept is largely abandoned today. Physicists prefer to keep mass invariant, the same in all frames, and instead describe the increase in energy and momentum directly. The famous equation E squared equals P squared C squared plus M squared C to the fourth ties together energy, momentum, and rest, mass without ambiguity. The outdated notion of mass changing with velocity has been replaced by a clearer understanding. Mass is constant, but energy grows without bound as you approach the speed of light. This shift in language emphasizes that what matters is the full four-vector of energy and momentum, not a redefined mass. A striking real-world example of time dilation comes from cosmic rays. High in the atmosphere, energetic particles strike molecules and create showers of muons. These muons have a proper lifetime of only about 2 microseconds, which should not allow them to reach the ground before decaying. Yet when measured, large numbers do arrive at Earth's surface. The explanation is that, from our perspective, their internal clocks tick more slowly because of time dilation. In their own frame, they live just as long as expected, but to us their lifetime is stretched enough to cross tens of kilometers. Every cosmic ray muon that reaches the ground is a natural demonstration of relativity in action. Radiation itself also changes character at high speeds due to relativistic beaming. As a source moves close to the speed of light, its emitted radiation no longer spreads evenly, but becomes concentrated in the forward direction. To an observer, the light appears brighter and bluer ahead of the motion, and dimmer behind. This effect is crucial in astrophysics, where jets from quasars or gamma-ray bursts appear intensely focused, their energy funneled into narrow cones by relativistic speeds. Beaming reminds us that not only do space and time bend under relativity, but even light reshapes its pattern of spread, sharpening into a spotlight aimed along the path of motion. Einstein built general relativity on one deceptively simple idea: the equivalence principle. Locally, the effects of gravity and acceleration are indistinguishable. If you are sealed inside an elevator, you cannot tell whether the force pressing you to the floor comes from being on Earth or from the elevator accelerating upward in deep space. Gravitational mass, which determines how strongly a body is pulled, and inertial mass, which determines how strongly it resists acceleration, are exactly equal. This equality elevates gravity from being a simple force to being geometry itself, the bending of space-time that guides motion. The equivalence principle is the seed from which the entire curved universe of relativity grows. When space-time curves, free-falling objects do not simply move independently, they reveal the structure of curvature through geodesic deviation. The geodesic is the natural straight-line path in curved space-time, but two nearby geodesics may diverge or converge depending on how space-time is warped. This deviation is what we feel as tidal forces. Drop two objects side by side toward Earth. Their paths are not perfectly parallel because each feels a slightly different pull toward the planet's center. The difference in acceleration is the tidal effect, a small-scale signature of the larger curvature of space-time. Near massive objects like black holes, this geodesic deviation becomes extreme, stretching and compressing objects with almost unimaginable force. The most iconic measure of gravity strength is the Schwarzschild radius. It sets the size of the event horizon for a non-rotating black hole and is given by R sub s equals 2gm divided by c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. For Earth, this radius would be less than 1 centimetre, for the Sun, about 3 kilometres. If an object is compressed within its Schwarzschild radius, light itself cannot escape, and the object becomes a black hole. The simplicity of this formula hides the enormity of its implications, that mass, space, and light can conspire to seal off a region of the universe forever. One of the most beautiful consequences of curved space-time is gravitational lensing. Light, which in flat space travels along straight lines, bends around massive objects as though space itself were a lens. Galaxies and clusters can warp the light of more distant galaxies behind them, producing arcs, rings, or multiple images. Sometimes this magnifies faint sources, letting astronomers glimpse objects far too dim to be seen otherwise. These cosmic lenses reveal both the distribution of visible matter and the hidden scaffolding of dark matter, which bends light without emitting any itself. What started as Einstein's thought experiment has become one of the astronomer's sharpest tools. General relativity is not only cosmic, it touches your daily life every time you use GPS. Satellites orbit Earth high above the surface, where gravity is weaker, and so their onboard clocks tick faster relative to clocks on the ground. At the same time, their high orbital speed introduces special relativistic time dilation, which slows them down. The combination means satellite clocks gain about 38 microseconds per day compared with Earth clocks. Without correcting for both special and general relativity, GPS errors would build up to kilometers of inaccuracy within a day. The fact that your phone can place you on a street corner with meter-scale precision is a direct consequence of Einstein's equations. Near a rotating mass, relativity predicts an even stranger effect: frame dragging. Space and time are not rigid. They are twisted by the rotation of massive bodies. This means that inertial frames, the invisible grids we use to measure motion, are dragged around in the direction of the spin. Around Earth, the effect is tiny but measurable, confirmed by missions such as Gravity Probe B. Around a rapidly spinning black hole, the effect is dramatic, forcing all objects near the horizon to rotate along with the hole. Frame dragging shows that rotation is not just a property of matter, but something that imprints itself onto the very fabric of space-time, twisting reality itself into a cosmic whirlpool. Black holes become even stranger when they rotate. The solution describing them, called the Kerr metric, predicts not only an event horizon, but also an outer region called the ergosphere. Inside this oblate, lens-shaped region, space itself is dragged so forcefully by the whole spin that no observer can remain still relative to the distant stars. Every object, even light, is compelled to rotate with the black hole. You could in principle hover in orbit just outside the ergosphere, but once you cross into it, motionless hovering becomes impossible. It is a cosmic treadmill where the space-time fabric itself is in motion. The ergosphere is not just peculiar, it offers a way to extract energy. This is the essence of the Penrose process. Within the ergosphere, an object can split into two fragments, with one falling into the black hole on a trajectory of negative energy as measured from infinity. The other fragment escapes carrying away more energy than the original object possessed. The extra comes from the rotational energy of the black hole itself, which is slowly spun down. In theory, this makes black holes the ultimate power plants. Though impractical for spaceships, astrophysical processes such as magnetic fields interacting with ergospheres may achieve similar energy extraction on a grand scale. If matter falls toward a black hole, it rarely plunges straight in. Instead, it forms a swirling accretion disk where friction and magnetic turbulence convert gravitational energy into heat and radiation. The efficiency of this process can exceed that of nuclear fusion. Burning hydrogen into helium converts about 0.7% of the mass into energy. Accretion onto a non-rotating black hole can reach efficiencies of around 6%, and onto a maximally rotating Kerr black hole, up to about 42%. In other words, a kilogram of matter falling into such a disk can release more energy than the same kilogram undergoing nuclear fusion in a star. This is why accreting black holes outshine entire galaxies despite being smaller than our solar system. The light from these disks is not steady but often flickers with quasi-periodic oscillations, rhythmic variations in X-ray brightness. These oscillations are thought to reflect the orbital and precession frequencies of gas close to the innermost stable circular orbit. By studying their patterns, astronomers probe the strong gravity regime right at the edge of black holes, where relativistic effects twist time and space. These oscillations are like seismic waves in space-time, carrying information about the hidden geometry of the deepest gravitational wells. When stars venture too close, the black hole's tidal forces can shred them in a tidal disruption event. The star is stretched into a stream of gas, much of which falls inward, creating a flare that can briefly outshine the host galaxy. These flares are cosmic fireworks announcing the presence of otherwise quiescent black holes. They also let astronomers weigh the black hole by studying the flare's brightness and evolution. In a sense, stars wandering too close are accidental probes, sacrificed to reveal the properties of the dark giant that destroyed them. On the larger scales, some black holes act not as silent consumers, but as engines driving colossal jets. Active galactic nuclei, powered by supermassive black holes millions or billions of times the mass of the Sun, launch streams of plasma at nearly the speed of light. These jets can stretch for millions of light years, far beyond their host galaxies. Magnetic fields, twisted by the rotation of the black hole and its disk, are thought to collimate and accelerate the plasma into narrow beams. Observed in radio, optical, and X-ray light, these jets shape galaxy evolution and seed intergalactic space with energy and matter. They are perhaps the most dramatic demonstration that black holes, paradoxically, can be among the brightest beacons in the universe, fire particles one at a time through a pair of slits, electrons, photons, even big molecules, and wait. Each quantum lands as a single dot on the screen, never half here and half there. But after many arrivals, a striped interference pattern emerges, the unmistakable fingerprint of waves. Close one slit and the stripes vanish. Open both and they return. Try to peek and learn which slit each quantum used, and the interference fades away. The lesson is not that particles are indecisive, but that the experiment itself defines what can be observed. Arrange it to reveal which path, and you get particles. Arrange it to reveal interference, and you get waves. With single quanta, the double slit compresses the mystery into sharp relief. Probability distributed like a wave, outcomes arriving as discrete impacts. To turn those wave-like amplitudes into actual chances, quantum theory uses the Born rule. Take the wave function, a complex value description of possibilities, and compute the probability by squaring its magnitude. In words, probability at a point equals the modulus squared of the amplitude at that point. Sum, or integrate, these probabilities over all space and you get 1, reflecting certainty that something happened somewhere. Interference arises because amplitudes add before squaring. Two positive amplitudes can reinforce, while amplitudes with opposite phase can cancel. This simple squaring rule is why a faint, coherent beam can produce the same bright and dark pattern as a loud one. The phase relations, not just the intensities, decide where outcomes accumulate. In quantum mechanics, every measurable quantity is represented by an operator acting on states, and the allowed outcomes are the operator's eigenvalues. Hermitian operators ensure those outcomes are real numbers. Some operators play nicely together, sharing a common set of ion states. Others refuse to commute, and their incompatibility is encoded in a commutator. Position and momentum are the canonical example. Their commutator equals I times h bar, which blocks the possibility of assigning both with arbitrary precision in the same state. Expectation values emerge from sandwiching operators between state vectors, read aloud as the expectation of A equals bra psi A ket psi, providing the average outcome over many trials without ever needing to imagine tiny billiard balls. Measurement adds a special rule. When you measure an observable, the state collapses onto one of that observable's eigenstates, with a probability given by the Born rule. This is the projection postulate. Before measurement, a system may be in a superposition, a weighted sum of possibilities. After measuring, the superposition vanishes, and the system is found in a definite outcome state, ready to evolve again under the Schrödinger equation until the next interrogation. Repeat the same measurement immediately, and you get the same result, because the state has been projected into that eigenbasis. Change what you measure, switch operators, and you generally rebuild a new superposition, and the roulette wheel of probabilities spins again. Not every state is pure or perfectly isolated. Density matrices, usually denoted ρ, describe both clean superpositions and statistical mixtures within one unified language. A pure state looks like ρ equals ket psi times bra psi, and satisfies ρ squared equals a ρ. A mixed state representing classical uncertainty or entanglement with unobserved surroundings has ρ squared not equal to ρ. Take a larger system and trace out the environment, perform the partial trace, and you obtain a reduced density matrix that captures everything you can still predict about the part you keep. Decoherence enters naturally here. Interaction with the environment suppresses off-diagonal terms in RAO, washing out interference and making superpositions look like classical mixtures without invoking any mystical forces. The density matrix view is the accountant that keeps clear books when systems refuse to stay alone. Finally, entanglement challenges any story in which distant systems carry pre-written instructions. Bell inequalities quantify what any local hidden variable theory would allow for correlated measurements on separated particles. Quantum mechanics predicts stronger correlations. Experiments violate Bell's bounds, with results exceeding classical limits up to the famous 2 times the square root of 2 in the CHSH form. The upshot is crisp. No theory that keeps influences strictly local and outcomes predetermined can reproduce the observed data. The world is not signaling faster than light. Relativity's speed limit on information stands, but nature's correlations are deeper than classical common sense allows. Entanglement is not a whisper sent across space. It is a pattern written into the joint state from the start, one that only reveals itself when measurements are compared. Quantum tunneling lets objects do what classical rules forbid: pass through energy barriers without having enough energy to climb over them. In alpha decay, a bound helium nucleus inside a heavy atom faces a repulsive Coulomb wall that is higher than its available energy. Classically, it would be trapped forever. Quantum mechanically, its wave function seeps into and through the barrier with a small but non-zero probability, and eventually the alpha particle appears outside and escapes. The same principle powers scanning tunneling microscopy, where a sharp metallic tip hovers a nanometer or so above a surface. Electrons tunnel across the vacuum gap, creating a current exquisitely sensitive to distance. Shift the tip by a fraction of an angstrom and the current changes dramatically. By scanning line by line, the microscope maps surfaces with near-atomic resolution, all thanks to the ghostly reach of quantum waves through barriers. The quantum Zeno effect shows how observation itself can hold a system in place. If you repeatedly measure a quantum system to ask, are you still in the initial state? Rapidly enough, you can slow or even freeze its evolution that would otherwise carry it into a different state. The intuition is that each measurement projects the state back onto the starting point with some probability, resetting the clock. In the limit of incessant checks, transitions are suppressed, like trying to watch a pot boil by opening the lid every instant and inadvertently preventing the build-up that would let it simmer over. In practice, experiments with atoms and qubits demonstrate that frequent gentle probes alter transition rates, turning measurement from a passive readout into an active control knob. Rabi oscillations are the clean rhythmic heartbeat of a two-level quantum system driven coherently. Shine a resonant field, microwaves on a superconducting qubit, radio frequency light on a nuclear spin, or laser light on an atom, and population sloshes back and forth between the two states in time, with a frequency set by the drive strength. Start in the ground state, and at half a Rabi period you're in the excited state. At a full period you're back where you began. By choosing the pulse duration precisely, a pi pulse or a pi over 2 pulse, you can prepare exact states or superpositions at will. This is the workhorse of quantum control and spectroscopy, a metronome that turns fields into precise rotations on the Bloch sphere. Interference in quantum mechanics does more than produce bright and dark bands on a screen. It can suppress outcomes that are perfectly allowed in classical mechanics. In a path integral view, a particle considers all possible routes from A to B, each carrying a complex amplitude. Paths can add with the same phase, reinforcing probability, or arrive with opposite phases, cancelling to nearly zero. Dark fringes are the visible scars of this cancellation. Places a classical particle could go, but a quantum particle rarely does, because alternative histories erase each other's likelihood there. Devices like interferometers and coherent electron transport structures harness this effect, steering particles by arranging faces so that unwanted routes cancel out and desired routes build up. In 2 dimensions, particles can be neither standard bosons nor standard fermions. They can be anyone's, whose exchange does not simply multiply the wave function by +1 or -1, but by a phase that can be any value between 0 and pi, or even enact more complex transformations in so-called non-abelian cases. The key is braiding. When one anyone loops around another in a 2-dimensional plane, the joint quantum state remembers the path in a way impossible in 3 dimensions. This exotic statistics emerges in systems like the fractional quantum Hall effect, where strong magnetic fields and low temperatures create topological order. Beyond pure fascination, anyons are enticing for quantum computing because braiding non-abelian anyons can perform logic operations that are inherently robust against many local errors. Topological insulators look paradoxical at first glance. They are electrical insulators in the bulk, but excellent conductors on their surfaces or edges. The reason lies in topology and symmetry. The interior has an energy gap like an ordinary insulator, but the surface hosts special states that cross the gap and are protected by the material's global properties, not by delicate tuning. Time reversal symmetry and strong spin-orbit coupling lock an electron spin to its direction of motion, a spin momentum locking that suppresses backscattering from ordinary impurities. Try to nudge an electron backward and you would have to flip its spin, which typical bumps cannot do, so the edge current flows with unusual resilience. These protected highways of conduction promise low dissipation electronics and provide a playground where condensed matter systems emulate high-energy physics in the lab. In the classical world, copying is effortless. A book can be photocopied, a file duplicated, a genetic sequence replicated by biology itself. But in quantum mechanics, the no-cloning theorem slams the door on perfect copying of unknown states. If you do not know a quantum state in advance, there is no physical process that can duplicate it exactly without disturbing it. This arises because cloning would require simultaneously preserving all the amplitudes and phases of a superposition, something forbidden by the linearity of quantum evolution. The theorem protects the security of quantum cryptography. Eavesdroppers cannot simply make stealthy duplicates of quantum keys. It also ensures that quantum information is precious. Once measured, it collapses, and once lost, it cannot be perfectly recreated. With no cloning allowed, quantum error correction takes a very different route from classical error correction. Instead of copying information, it spreads it non-locally across multiple qubits in such a way that errors can be detected and reversed without revealing the encoded state. Surface codes, Steen codes, and others weave entanglement patterns that make the logical information resistant to local noise. A single qubit's delicate state may flip or lose coherence, but the global correlations across dozens of physical qubits preserve the logical bit intact. This strange redundancy, where information is nowhere yet everywhere, is the lifeline that makes large-scale quantum computing feasible. It is the art of safeguarding quantum whispers against the roar of the environment. Quantum annealing takes another quantum trick, tunneling, and uses it to explore difficult energy landscapes. Imagine a problem encoded as a rugged terrain, full of valleys and hills. A classical algorithm like simulated annealing must climb out of valleys to find the lowest one, often getting stuck. Quantum annealing instead allows the system to tunnel through barriers, bypassing climbs that would be prohibitive. By gradually reducing quantum fluctuations, the system settles into a low-energy state that ideally represents the solution. Companies building quantum annealers target optimization tasks in finance, logistics, and material science, where the problem is not arithmetic but searching a near-infinite landscape of possibilities. Quantum sensing leverages the exquisite sensitivity of superposition and interference. Atom interferometers split and recombine atomic wave functions, with the interference fringes shifting in response to tiny accelerations or rotations. Because atoms are massive, their de Broglie wavelengths are tiny, giving them remarkable sensitivity compared with photons. Such sensors can measure gravitational acceleration to parts per billion, map underground structures by detecting mass anomalies, or track navigation without GPS by reading the subtle twists of space-time on quantum waves. The same principles power optical clocks, which use laser-cooled atoms to define time with such precision that they can detect relativistic time dilation from standing a few centimeters higher or lower in Earth's gravitational field. Quantum information is not restricted to discrete two-level systems. Continuous variable approaches use quantum states of light, such as squeezed states, where uncertainty in one quadrature of the electromagnetic field is reduced below the usual quantum limit at the expense of the other. Homodyne detection, mixing these delicate states with a strong reference beam, lets experimenters extract information with high efficiency. This framework offers natural compatibility with existing optical communication infrastructure, making it a promising route for quantum communication. Instead of qubits, it deals with modes, amplitudes, and phases, blending quantum strangeness with the smoothness of classical waves. One of the most striking demonstrations of quantum connectivity is entanglement swapping. Suppose particle A is entangled with particle B and particle C is entangled with particle D. If you perform a joint measurement on B and C, projecting them into an entangled basis, the measurement outcome instantly entangles A and D, even though they have never interacted. Entanglement has leapt across the network, forged by the act of measurement itself. This process underlies the concept of quantum repeaters, essential for building long-distance quantum communication links. It turns entanglement into a resource that can be stretched, swapped, and woven into networks, creating correlations that classical physics simply cannot reproduce. Some atoms live life on a grand scale, at least by quantum standards. Rydberg atoms are atoms where one electron has been excited to a very high principal quantum number, meaning it orbits far from the nucleus. The size of these orbits grows with the square of the quantum number, so at values of 50 or 100, the atom can be hundreds of nanometers across, millions of times larger than a hydrogen atom in its ground state. These giants are incredibly sensitive. Their polarizability, the ease with which their electron cloud distorts in an electric field, is exaggerated to extremes. This makes them perfect playgrounds for studying quantum interactions, because even faint external fields or tiny collisions leave detectable marks. Not every jump between atomic states is allowed, though, and that is where selection rules come in. These rules arise from conservation of angular momentum and parity. For example, in an electric dipole transition, the orbital angular momentum quantum number must change by plus or minus 1, and parity must flip. This is why certain spectral lines are bright while others are missing entirely, even though energy levels exist. The rules ensure that atoms respect symmetry constraints when interacting with light, turning what might seem like a chaotic zoo of transitions into a disciplined dance. Violations can occur through higher-order processes such as magnetic dipole transitions, but these are far weaker. Selection rules are the filters that let us read atomic spectra as clear fingerprints rather than unreadable scribbles. Look closer at those fingerprints, and you notice that single lines often split into multiples. Fine structure arises from relativistic corrections to electron motion and the coupling between an electron's spin and its orbital motion. Hyperfine structure goes further, including interactions between the electron cloud and the magnetic moment of the nucleus itself. These splittings are small compared to the main energy gaps, but are crucial in high-precision physics. The cesium hyperfine transition, for instance, defines the second in the International System of Units. By zooming in on fine and hyperfine structure, scientists unlock not only atomic detail, but also new standards for measurement and tests of fundamental physics. When molecules vibrate and rotate, they also leave signatures in light. Vibrational transitions typically occur in the infrared, while rotational transitions fall into the microwave band. Together they form the backbone of molecular spectroscopy. Each molecule has its own pattern, determined by its bonds, masses, and geometry, so infrared absorption spectra serve as molecular fingerprints. Astronomers use these patterns to identify molecules in interstellar clouds, while chemists use them to analyze unknown samples. Even our bodies are tuned to these wavelengths. The greenhouse effect works in large part because carbon dioxide, water vapor, and methane absorb infrared radiation from Earth's surface, trapping heat in the atmosphere. Raman scattering offers another window into molecular vibrations, but in a subtler way. When light interacts with a molecule, most photons scatter elastically with no change in frequency. A small fraction, however, emerge shifted, having gained or lost energy equal to a vibrational quantum of the molecule. These shifts, called Stokes and anti-Stokes lines, reveal vibrational modes without requiring the molecule to absorb infrared directly. Raman spectroscopy thus complements infrared absorption, accessing different vibrational symmetries and providing richer information. It is widely used in chemistry, biology, and materials science, often with lasers as the light source, turning faint frequency shifts into powerful probes of structure. Perhaps the most astonishing control over atoms comes from laser cooling. By tuning laser light slightly below an atomic resonance, atoms moving toward the beam see the light Doppler shifted into resonance, absorb a photon, and slow down. Repeated absorption and re-emission saps their kinetic energy, effectively cooling them. With counter-propagating beams in 3 dimensions, atoms can be trapped in an optical molasses where their temperature plummets to microkelvin scales. Add magnetic fields, and the system becomes a magneto-optical trap, holding atoms nearly motionless. This technology has enabled Bose-Einstein condensates, atomic clocks of unprecedented precision, and experiments that push quantum mechanics into regimes unimaginable only decades ago. In crystals, electrons do not move as if they were tiny free particles darting through empty space. Instead, they feel the periodic landscape of the lattice, which reshapes their response to forces. To describe this, physicists use the idea of effective mass. It is not the true mass of the electron, but a parameter that reflects how the electron's energy varies with momentum inside a band. In some directions it can be heavier, in others lighter, and in certain exotic materials it can even be negative. This concept allows us to treat complex quantum motion as if it were simple classical motion with a different inertia. Effective mass is why electrons in silicon respond sluggishly compared with those in gallium arsenide, making one material better for general computing and the other for high-speed devices. The electrical conductivity of a material, denoted sigma, depends on 2 key ingredients: how many carriers there are and how easily they move. The equation sigma equals times q times mu captures this, where n is the carrier density, q is the charge of each carrier, and mu is the mobility. A metal like copper has a very high carrier density and high mobility, giving enormous conductivity. A semiconductor can have its carrier density tuned by doping, adding atoms with extra or fewer electrons, or by gates in modern devices. That ability to tune sigma is what makes semiconductors the foundation of electronics. They are neither locked into conducting everything like a metal, nor refusing to conduct like an insulator, but can be precisely engineered for purpose. Sometimes electron behavior in solids becomes quantized in startling ways. The quantum Hall effect, discovered in the late 1970s, showed that under very strong magnetic fields and very low temperatures, the Hall conductance, the sideways response of electrons to an applied current, does not vary smoothly, but jumps in exact steps. Each step equals an integer multiple of e squared over h, the square of the electron charge divided by Planck's constant. This precision is so perfect that the effect is used as a standard of resistance in metrology. Later, the fractional quantum Hall effect revealed even stranger behavior, where electron interactions create quasi-particles with fractional charge, opening the door to the exotic world of anyone's and topological order. Solid-state physics is also the engine behind solar power. Photovoltaics take in light and turn it into electricity by separating charge carriers. In a solar cell, photons with enough energy excite electrons across the bandgap of a semiconductor, creating electron-hole pairs. A built-in electric field at a junction then sweeps the electrons one way and the holes the other, producing a current that can be harvested. The choice of materials, the width of the bandgap, and the efficiency of charge separation all determine how much sunlight is converted into usable energy. From rooftop panels to massive solar farms, photovoltaics rest on the quantum fact that light can knock carriers free and an electric field can put them to work. The same principle of coupling heat and charge underpins thermoelectrics. The Seebeck effect generates a voltage when one side of a material is hotter than the other, as carriers diffuse unevenly. Flip the process, and driving a current produces heating on one side and cooling on the other, known as the Peltier effect. These twin effects allow devices that turn waste heat into electrical power or that function as compact solid-state coolers with no moving parts. The challenge is efficiency. Good thermoelectrics must conduct electricity well but heat poorly, a combination that is hard to achieve. Still, progress in nanostructured materials has made them increasingly practical for harvesting energy from everyday temperature gradients. Another clever use of solid-state behavior comes from ferroelectrics. These are materials whose internal electric polarization can be flipped by applying an external electric field. Picture countless tiny dipoles inside a crystal, all pointing in a preferred direction. With a strong enough field, they can be reoriented, switching the polarization between distinct states. Because the material retains its polarization even after the field is removed, ferroelectrics can store binary information in a durable way. They offer non-volatile memory that could complement or even rival existing storage technologies. Beyond memory, their sensitivity to fields makes them useful in sensors and actuators, where the alignment of charges drives macroscopic effects. In ferroelectrics, the hidden geometry of atomic displacements translates directly into functional technology. In ordinary metals, electrons act like individuals, bouncing off atoms and losing energy as heat. But in superconductors, electrons pair up into bound states called Cooper pairs. This pairing seems counterintuitive, since electrons repel each other, but vibrations in the crystal lattice can create an effective attraction. Once paired, the electrons condense into a single, macroscopic quantum state that flows without resistance. Instead of trillions of separate particles, the system behaves like one collective wave function spread across the entire material. This coherence means current can circle a superconducting loop indefinitely without ever fading, a feat utterly impossible in normal conductors. A striking signature of superconductivity is the Meissner effect, the complete expulsion of magnetic fields from the interior of the material. If superconductors were merely perfect conductors, they would trap magnetic fields in place rather than pushing them out. The Meissner effect shows that superconductivity is not just zero resistance, but a new phase of matter with its own rules. Place a magnet above a superconductor cooled below its critical temperature, and the exclusion of the field causes the magnet to levitate, suspended on invisible quantum currents. It is a classroom demonstration that never fails to look like magic, though it is physics at work. In Type II superconductors, magnetic fields are not expelled entirely, but thread their way through in narrow quantized tubes of flux called vortices. Each vortex carries exactly 1 unit of magnetic flux, equal to Planck's constant divided by twice the electron charge. These flux lines arrange themselves in regular lattices, visible under microscopes, giving a crystalline beauty to quantum magnetism. The discreteness of flux quantization makes superconductors ideal for devices like superconducting quantum interference detectors, or SQUIDs, which can measure tiny magnetic fields with exquisite precision. What looks continuous in classical electromagnetism becomes grainy under quantum rules, even for magnetic fields themselves. The Josephson effect is another marvel. Place 2 superconductors close together, separated by a thin insulating barrier, and Cooper pairs can tunnel across. The resulting current depends on the phase difference between the 2 superconducting wave functions. Apply a constant voltage across the junction, and the phase wins steadily, producing an alternating current that oscillates at a frequency directly proportional to the voltage. This is no ordinary oscillation, but one tied to fundamental constants. Frequency equals 2 electron charges divided by Planck's constant times the voltage. The precision of this relation allows Josephson junctions to serve as voltage standards, anchoring electrical units to the bedrock of quantum mechanics. Superfluidity extends similar quantum principles to liquids. In liquid helium, for example, cooling below a critical temperature produces a state that flows without viscosity. Stirring a container does not create swirling eddies like in water, but instead forms quantized vortices, each with circulation equal to Planck's constant, divided by the mass of the helium atom. These vortices cannot simply smear out. Their topological features, locked into discrete amounts of angular momentum. Watching them arrange into lattice patterns is like seeing a liquid obey the rigid rules of quantization, usually reserved for atoms and photons. Helium-3, an isotope with 2 protons and 1 neutron, achieves superfluidity in a different and more exotic way. Because its atoms are fermions, they cannot all occupy the same state directly. Instead, they form pairs with non-zero angular momentum, p-wave pairing, analogous to but richer than the s-wave Cooper pairing in conventional superconductors. The order parameters describing this state are complex, with multiple components reflecting spin and orbital symmetries. The result is a superfluid with different phases, each with distinct textures and excitations, almost like a condensed matter laboratory for high-energy physics. Helium-3 superfluidity reveals how deeply quantum mechanics shapes matter, not only at the smallest scales but in entire macroscopic fluids that move in ways our intuition never prepared us for. One way to understand the nucleus is to picture it as a droplet of quantum liquid. The liquid drop model treats nucleons, protons and neutrons, as if they were particles bound together by surface tension, much like molecules in a drop of water. This approach explains broad features such as the approximate binding energy, the role of surface effects, and the tendency for large nuclei to deform and fission. But nuclei are not just featureless drops. They also show sharp, magic numbers, where they are exceptionally stable, like closed shells of electrons in atoms. Here the shell model takes over, describing protons and neutrons as moving in quantized orbits within the nuclear potential. The liquid drop picture captures the bulk, while the shell model reveals the fine structure, and together they give us a remarkably complete portrait of nuclear behavior. Binding energy, the glue that holds nuclei together, has its own story to tell. If you plot binding energy per nucleon against atomic mass, it rises steeply from hydrogen and helium, peaks around iron and nickel, and then slowly declines for heavier elements. This curve explains why stars shine and why nuclear power works. Fusion of light nuclei up to iron releases energy because the resulting nuclei are more tightly bound. Conversely, fission of heavy nuclei like uranium also releases energy, because splitting them into smaller fragments brings the pieces closer to the peak of stability. The universe itself runs on this curve. Stars fuse light elements until they reach iron, beyond which no further energy can be gained, leading ultimately to their collapse. Harnessing fission energy in reactors depends on subtle nuclear dynamics. Neutrons produced in fission are born fast, with energies of millions of electron volts, but uranium-235 and other fissile isotopes absorb slow neutrons much more readily. To bridge this gap, reactors employ moderators, materials like water, heavy water, or graphite, that slow neutrons through repeated collisions without capturing them. These moderated neutrons then sustain the chain reaction with far greater efficiency. Moderation is the quiet balancing act at the heart of thermal reactors, making the difference between a runaway burst and a controlled, steady release of energy. Nuclear transformations also give us a clock for dating the past. Radiometric dating uses isotopes with known half-lives, such as carbon-14, uranium-238, or potassium-40. By measuring the ratio of parent to daughter isotopes in a sample and comparing it to the known decay rates, scientists can calculate ages from thousands to billions of years. This method has dated archaeological finds, the age of Earth itself, and even meteorites from the dawn of the solar system. Half-life is the key. The steady statistical rhythm of decay becomes a cosmic timepiece, ticking away across eons. Among the most elusive participants in nuclear physics are neutrinos. These nearly massless particles interact so weakly that trillions pass through your body every second without leaving a trace. To catch even a few, detectors must use enormous targets, vast underground tanks filled with water or heavy liquid, lined with sensitive light detectors that watch for the faint flashes produced when a rare neutrino does interact. Experiments like Super Kamiokande in Japan or Ice Cube in Antarctica reveal neutrinos from the Sun, from supernovae, and from distant cosmic accelerators. Each captured neutrino is a messenger from processes otherwise invisible to us, offering glimpses into both astrophysics and fundamental physics. Finally, the story of how elements beyond iron are forged points to the violent corners of the cosmos. The rapid neutron capture process, or R process, occurs when a nucleus is bombarded with neutrons so quickly that it climbs up the nuclear chart before it can decay. This requires extreme environments with vast neutron fluxes, such as supernova explosions or the mergers of neutron stars. The R process produces gold, platinum, uranium, and many other heavy elements that cannot be made in ordinary stellar burning. The jewellery we wear, the rare elements in our electronics, and the actinides in nuclear fuel are all relics of cataclysmic cosmic events, reminders that some of the most valuable materials on Earth were born in the deaths and collisions of stars. The building blocks of matter dive deeper than protons and neutrons. Inside them live quarks, which come in 6 flavours whimsically named up, down, charm, strange, top, and bottom. Each flavour also comes in 3 colours, not literal shades but a label for the charge of the strong interaction. Yet quarks are never found alone. They are confined into combinations called hadrons, baryons like the proton and neutron, which hold 3 quarks, and mesons, which pair a quark with an antiquark. The rule is strict. Only colourless combinations make it into the observable world. Quarks are thus permanent prisoners of their own force, forever locked together in groups. The agents keeping them bound are gluons, the carriers of the strong force. Unlike photons, which ignore one another, gluons themselves carry colour charge and can interact directly. This self-interaction creates the peculiar property of confinement. At low energies, the strong force does not weaken with distance but grows, ensuring quarks can never drift apart. Try to pull them, and the energy you invest spawns new quark-antiquark pairs, which bind into fresh hadrons before any quark can escape. Paradoxically, at very high energies, the strong force runs the other way, becoming weaker, a phenomenon called asymptotic freedom. This is why inside a high-energy collider, quarks briefly behave almost like free particles before showering into jets of hadrons. Other forces govern rarer processes. The weak interaction, mediated by the W and Z bosons, is responsible for beta decay and the transmutations that fuel the sun. Unlike photons, which are massless, the W and Z are heavy, roughly 90 times the mass of a proton. Their heft shortens their range to a scale smaller than the diameter of a nucleus, explaining why weak interactions are so rare. Yet without them, the universe would lack the chain of nuclear reactions that lights the stars and forges the lighter elements. the names W and Z, originally chosen simply as convenient labels, now stand as symbols of one of nature's essential forces. The reason these bosons have mass at all is the Higgs mechanism. In the early universe, before symmetry breaking, the equations of the electroweak force described all particles as massless. Then, as the Higgs field acquired a non-zero vacuum expectation value, it provided a medium through which certain particles interact and thus gain inertia. The W and Z bosons, otherwise massless, became heavy. Fermions such as quarks and leptons couple to the Higgs field too, picking up their varied masses. Only the photon and gluon remained untouched, staying massless. The discovery of the Higgs boson at CERN in 2012 confirmed this picture, giving substance to the theory that mass itself arises from a cosmic field suffusing all of space. Within this framework lies another layer of subtlety. Particles do not stay neatly confined to a single flavour. Quarks mix when they change identity under the weak interaction, described mathematically by the Kabibo-Kobayashi-Maskawa, or CKM matrix. Similarly, neutrinos, once thought to be massless, oscillate between electron, muon and tau flavours as they travel, described by the Pontecorvo-Maki-Nakagawa-Sakata, or PMNS matrix. These mixing matrices encode the probabilities of flavour transformations, giving rise to phenomena like neutrino oscillations that have been directly observed. They reveal that even fundamental particles live fluid identities, changing costume as they move through the universe. Finally, buried in the details of these mixings lies an asymmetry that may explain why matter exists at all. CP symmetry, the idea that flipping particles to antiparticles and reflecting them in a mirror should leave the laws of physics unchanged, is slightly violated. The weak interaction treats matter and antimatter differently in subtle but measurable ways. Though small, this CP violation may have tipped the balance in the early universe, allowing a tiny excess of matter over antimatter to survive after annihilations. Without it, we would be adrift in a universe of radiation with no stars, no planets, and no observers. The slight skew in the cosmic dice toward matter is why there is something rather than nothing. The expansion of the universe is not guessed at. It is governed by the Friedmann equations, which are Einstein's field equations, specialized to a homogeneous isotropic cosmos. They relate the square of the Hubble expansion rate to the energy content and spatial curvature. In words, h squared equals 8 pg over 3 times the total energy density minus kc squared over a squared, where a is the scale factor and k is the curvature, constant taking values plus 1, 0 or minus 1. A second equation tells how the acceleration of the scale factor depends on pressure as well as energy density. A double dot over S equals minus 4, pg over 3 times, the quantity Rho plus 3p over c squared. Matter slows expansion because it has positive density and negligible pressure. Radiation slows it even more because it adds pressure. A cosmological constant with negative pressure does the opposite, driving acceleration. Package each component into a density parameter omega, compare to the critical density, and the geometry, fate, and tempo of the universe all fall out of these compact relations. Long before galaxies assembled, the young universe rang like a drum, and we can still see its faint afterglow as the cosmic microwave background. This light is not perfectly uniform. It carries temperature anisotropies at the level of a few parts in 100,000 that trace primordial density ripples, map those hot and cold spots across the sky, and you read a power spectrum of acoustic peaks whose positions and heights reveal the universe's contents. How much ordinary matter, how much dark matter, how much radiation, and its geometry. The first peak pins down near flat spatial curvature. The relative heights of the first and second peaks diagnose baryon content. Later peaks tell you about diffusion damping and the thickness of the last scattering surface. With a single panorama of microwaves at about 2.725 kelvins, cosmology turns the infant universe into a precision laboratory. Those same primordial sound waves left another fossil in the distribution of galaxies, baryon acoustic oscillations. As the early plasma cooled and photons decoupled, the outward propagating sound waves froze, imprinting a preferred separation scale in matter. Billions of years later, galaxy surveys reveal a very gentle excess probability of finding pairs of galaxies separated by roughly 150 megaparsecs in co-moving distance. That scale acts as a standard ruler. Measure how big it looks at different redshift, across the sky and along the line of sight, and you recover the universe's expansion history, much as a familiar coin of known size lets you judge distance in a photograph. Bayo is quiet, statistically subtle, but it's one of the most robust yardsticks in all of cosmology. Dark matter does not shine, but gravity makes its presence undeniable. Starting from the tiny overdensities seen in the microwave background, dark matter collapses first because it does not feel radiation pressure or electromagnetic forces. It forms a cosmic scaffolding of halos and filaments, a web onto which gas falls, cools and ignites into galaxies and stars. N-body simulations that include only gravity and cold, slow-moving dark matter reproduce the observed large-scale structure astonishingly well. Vast voids, sheets and clusters emerge from simple initial conditions. On galactic scales, dark matter halos explain flat rotation curves and the lensing of background galaxies. It is the invisible architecture of the universe, shaping what we see without ever directly catching the light. A different, more mysterious ingredient steers the late-time expansion: dark energy. Observations of distant Type Ia supernovae, combined with a cosmic microwave background and galaxy surveys, show that the expansion of the universe is accelerating. The simplest explanation is a cosmological constant, usually written as capital lambda, which behaves like a uniform energy density with negative pressure. In the Friedmann acceleration equation, this negative pressure term reverses the deceleration and drives acceleration. Whether dark energy is truly a constant or a slowly evolving field remains an open question, but its measurable effect is clear. It dilutes the growth of structures, alters the distance-redshift relation, and will, if constant, lead to a future where galaxies slip forever beyond our horizon. Alongside photons, the cosmos is suffused with an even more elusive relic, the cosmic neutrino background. When the universe was less than 1 second old, neutrinos decoupled from the primordial plasma and have been freely streaming ever since. Their temperature today should be a bit cooler than the microwave background, about 1.95 kelvins, because electrons and positrons later heated the photons during their annihilation. Although these relic neutrinos are extraordinarily hard to detect directly, their presence subtly influences cosmic evolution. They affect the expansion rate in the early universe, leave fingerprints in the pattern of microwave anisotropies, and slightly suppress the growth of small-scale structure due to their large thermal velocities. They are the quietest chorus in the cosmic symphony, heard not by our ears but by their gravitational effects written into the sky. The energy that makes stars shine comes from nuclear fusion, but the root depends on mass. In stars like our Sun and lighter, the proton-proton chain dominates. 2 protons fuse to form deuterium, which then combines with another proton to make helium-3, and through further reactions helium-4 is built. Each step releases energy in the form of gamma rays, neutrinos, and kinetic energy of particles. In stars more massive than about 1.5 times the Sun's mass, higher core temperatures allow a different cycle to take over. the carbon-nitrogen-oxygen, or CNO cycle. Here, carbon and oxygen nuclei act as catalysts, enabling protons to fuse more efficiently at high temperatures. Both processes end up turning hydrogen into helium, but the details matter for stellar evolution because the balance of reactions sets how a star lives and dies. The relation between a star's mass and its brightness is dramatic. The mass-luminosity relation says that luminosity scales roughly as mass to the power of 3 or 4. Double the mass, and the luminosity rises about 8 to 16 times. This disproportionate brightness means that massive stars burn through their nuclear fuel much faster, despite having more of it. A star 10 times the Sun's mass shines tens of thousands of times more brightly, but lives only tens of millions of years compared to the Sun's comfortable 10 billion year lifetime. In the cosmos, bigger does not mean longer lasting. It means a shorter, more brilliant existence, like a firework that exhausts itself quickly. As hydrogen in the core is consumed, a star evolves into a red giant. With the core filled with inert helium and unable to fuse at first, hydrogen burning shifts to a shell around the core. The envelope expands and cools, turning the star red and swollen. In low-mass stars, the core becomes degenerate, meaning pressure comes from quantum mechanics rather than temperature. When helium finally ignites in a so-called helium flash, degeneracy is lifted and the star settles into a new equilibrium. Shell burning and core burning alternate in layers as the star ages, creating an onion-like structure of fusion zones that set the stage for the final act. Some endings are especially dramatic. Type Ia supernovae occur when a white dwarf in a binary system accretes material from a companion until it approaches the Chandrasekhar limit of about 1.4 solar masses. At this threshold, electron degeneracy pressure can no longer support it, and carbon fusion ignites uncontrollably throughout the star. The result is a thermonuclear runaway that tears the white dwarf apart in a colossal explosion, leaving no remnant behind. Because the conditions are always similar, Type Ia supernovae reach nearly uniform peak brightness, making them reliable standard candles for measuring cosmic distances. It was observations of these explosions in the 1990s that revealed the accelerating expansion of the universe. Massive stars end differently in core collapse supernovae. Once fusion builds an iron core, no further energy can be gained by fusion, since iron has the highest binding energy per nucleon. The core collapses under gravity, densities soar to nuclear values, and protons and electrons merge into neutrons, releasing a flood of neutrinos. The collapse halts when matter becomes incompressible, and the core rebounds, sending a shock wave outward. Neutrino heating, an enormous outpouring of neutrino energy absorbed by the surrounding material, helps revive and drive the shock, blasting the star's outer layers into space. The explosion seeds the cosmos with heavy elements and leaves behind either a neutron star or a black hole. What remains after collapse depends on the physics of neutron matter, encoded in the neutron star equation of state. Neutron stars are only about 20 kilometers across, but pack more mass than the Sun into that volume. The maximum mass they can support before collapsing to a black hole depends on how neutrons and possibly exotic particles behave at densities beyond nuclear saturation. Observations of neutron stars in binary systems and of gravitational waves from mergers give clues, suggesting a maximum mass around 2 to 3 solar masses. Their radius, cooling behavior, and spin are all fingerprints of the unknown physics deep inside. These stellar remnants are cosmic laboratories for matter at its most extreme, bridging astrophysics, nuclear physics, and relativity. Neutron stars, the collapsed remnants of massive stars, can spin hundreds of times per second and carry magnetic fields trillions of times stronger than Earth's. When these fields channel streams of charged particles outward, beams of radiation emerge from their magnetic poles. If the star's spin axis and magnetic axis are misaligned, those beams sweep across the sky like the light from a cosmic lighthouse. To us, each sweep is seen as a pulse of radio waves, X-rays, or gamma rays. These pulses are astonishingly precise clocks, their rotation rates so stable that we can detect slowdowns caused by energy loss over decades. Some even glitch suddenly, spinning faster as interior superfluid regions transfer angular momentum to the crust, giving us a glimpse of physics under conditions far beyond terrestrial laboratories. Among neutron stars, a rarer class takes magnetic power to extremes. Magnetars boast fields 1,000 times stronger than those of ordinary pulsars, reaching up to around 10 to the power of 15 Gauss. In such titanic fields, atomic structures are stretched into thin spindles, and the stresses on the star's crust can trigger violent starquakes. These in turn release energy as giant flares, some of the brightest high-energy outbursts ever recorded in our galaxy. A single flare from a magnetar can momentarily outshine all other sources in the Milky Way. Though short-lived, magnetars show how magnetic energy can rival gravitational energy in shaping the behavior of compact objects. Not all high-energy messengers come neatly pulsed. Cosmic rays bombard Earth from all directions, spanning a breathtaking energy range. At the low end, they are protons and nuclei accelerated in supernova remnants and other shock fronts. At the highest end, exceeding 10 to the power of 20 electron volts, their origins remain partly mysterious. Jets from active galactic nuclei and shock waves in galaxy clusters are prime suspects. These particles can travel millions of light years, bent by intergalactic magnetic fields, before colliding with our atmosphere and producing air showers of secondary particles. The sheer energy of the most extreme cosmic rays is so great that a single proton can rival the kinetic energy of a baseball thrown at Major League speed. When charged particles spiral at relativistic speeds through magnetic fields, they emit synchrotron radiation. This process produces a broad spectrum of light, from radio waves to X-rays, with a distinctive polarization and power law distribution. Synchrotron emission explains the glow of radio galaxies, the arcs of supernova remnants, and the afterglows of gamma-ray bursts. Its reach is wide. The very same mechanism underlies the operation of human-built synchrotrons, where beams of electrons accelerated near the speed of light produce intense X-rays used for studying materials and biological molecules. Nature and laboratories both exploit the same physics, differing only in scale. Photons too can borrow energy from fast-moving electrons in a process called inverse Compton scattering. In ordinary Compton scattering, a photon collides with an electron and loses energy. But if the electron is moving at relativistic speeds, the photon can rebound with far greater energy than it had before. Soft photons, such as those from starlight or the cosmic microwave background, can be boosted to X-ray or gamma-ray energies this way. In astrophysical jets, this process complements synchrotron emission, together shaping the spectra we observe from blazars and other extreme systems. Inverse Compton scattering shows how electrons can turn low-energy light into the brightest beacons of the cosmos. In the highest energy regimes, light itself can create matter. When a gamma-ray photon with enough energy passes near a nucleus or a strong electromagnetic field, it can transform into an electron-positron pair. This process, called pair production, turns pure radiation into mass. The threshold requires energy greater than 2 times the electron rest mass, about 1.02 mega-electron volts. But in astrophysical contexts, gamma rays often exceed this easily. Near black holes and neutron stars, pair production shapes the surrounding plasma, filling magnetospheres with cascades of particles. In particle accelerators, it provides one of the cleanest demonstrations of Einstein's famous equation, E=mc², in action. Energy condensed into matter, fleeting yet undeniable. One of the most striking lessons of nonlinear science is that determinism does not guarantee predictability. Chaotic systems follow precise mathematical rules, but they also exhibit sensitive dependence on initial conditions. Two states that start almost indistinguishably close will diverge exponentially in time, so that after a while their fates are entirely different. This is popularly known as the butterfly effect, where the flap of wings in one place might alter the path of a storm elsewhere weeks later. The equations are not random, but the outcomes become effectively unpredictable after long enough, because no measurement of the starting conditions can ever be infinitely precise. Determinism in chaos is like writing with perfect penmanship on paper that magnifies every tremor of the hand. To make sense of this complexity, physicists turn to phase space, where all possible states of a system are plotted as points defined by both position and momentum. The resulting trajectories form portraits that reveal the geometry of motion. A pendulum without friction traces a closed loop, a limit cycle represents self-sustaining oscillations, and chaotic systems weave tangled paths around strange attractors. These attractors are neither single points nor neat loops, but fractal-like structures, where trajectories linger without ever repeating exactly. Looking at phase space, one sees chaos not as messy randomness, but as intricate order, etched in shapes too complex to be written in words alone. As systems are tuned toward chaos, they often follow a universal route: period doubling. Start with a simple oscillation, and as a control parameter changes, the system flips into oscillations that repeat every 2 cycles, then every 4, then every 8, and so on, with the intervals shrinking geometrically. The ratios of these intervals converge to the same numerical value no matter the system, about 4.669, known as the first Feigenbaum constant. This universal scaling law emerges in dripping faucets, electronic circuits, and biological rhythms alike. The discovery that such unrelated systems all follow the same numerical script was one of the great unifying revelations of chaos theory. Continuous dynamics can be bewilderingly complicated, so Henri Poincaré introduced a clever simplification, the Poincaré section. By slicing the continuous flow of a system at regular intervals, or at specific crossing points, the motion is reduced to a discrete map. Instead of tracing endless curves, you study a sequence of dots. This perspective reveals hidden structures, stable fixed points, nested tori, and scattered chaotic seas. In celestial mechanics, for example, Poincaré sections show the fine balance between regular planetary orbits and chaotic scattering trajectories. They are snapshots that turn a swirling storm of motion into a map one can study and classify. Even in the midst of chaos, not everything is lost. The Kolmogorov-Arnold-Moser theorem, or KAM theorem, shows that many quasi-periodic orbits in Hamiltonian systems survive small perturbations. Imagine planetary systems. One might expect even the slightest gravitational nudge from other planets to wreck the delicate clockwork. Instead, many orbits persist, slightly deformed but stable, because the irrational ratios of their frequencies resist resonance. The KAM theorem explains why the solar system has endured for billions of years, despite constant gravitational interactions. Chaos lurks in some regions, but islands of order remain, protected by number theory hidden in the equations of motion. Sometimes, surprisingly, randomness can actually help. Stochastic resonance describes cases where adding noise to a system makes its response to weak signals clearer. Consider a threshold system, like a particle in a double well potential that needs a nudge to hop over the barrier. A faint periodic signal on its own might be too weak to do the job. Add the right level of noise, however, and the particle begins to hop in sync with the signal, amplifying its effect. Too little noise does nothing. Too much drowns the signal entirely. Just the right amount creates order out of noise. This counterintuitive effect has been observed in physics, climate cycles, and even sensory biology, where a touch of randomness sharpens perception. Chaos and noise, once thought to be enemies of clarity, turn out to be partners in creating new forms of order. In physics, symmetry is more than aesthetic. It is the engine of conservation laws. Emmy Noether's theorem, proved in 1915, established the profound link between continuous symmetries and conserved quantities. If the laws of physics look the same at all times, then energy is conserved. If they look the same everywhere in space, then momentum is conserved. If they look the same in every direction, then angular momentum is conserved. This elegant bridge between geometry and dynamics underpins almost all of modern physics. What once seemed like separate facts, energy never disappears, momentum is constant, are actually shadows cast by deeper symmetries in the fabric of the universe. But symmetries can break, sometimes spontaneously. A system may have symmetric laws but settle into a state that picks a direction. Think of a pencil balanced on its tip. The underlying rules are rotationally symmetric, but once it falls, the symmetry is broken by the chosen direction. In quantum field theory, spontaneous symmetry breaking produces massless excitations called Goldstone modes. These appear, for example, as collective waves in ordered systems like spin waves in magnets. If the symmetry is gauged, tied to a force field, then the Goldstone modes can be absorbed, giving mass to gauge bosons. This is the mechanism by which the Higgs field gives the W and Z bosons their mass. The broken symmetry reshuffles the degrees of freedom, hiding massless modes and leaving behind massive particles. When symmetries break in space, they can leave scars called topological defects. These are not flaws, but stable structures encoded by how order parameters wrap around. In a superfluid, circulation is quantized into vortices where the phase wins by multiples of 2π. In liquid crystals, domain walls separate regions of different orientation, while in cosmology, models predict cosmic strings and monopoles forming during early universe phase transitions. Such defects are robust because they are protected by topology. You cannot smooth them away without cutting or tearing the field's configuration. They are nature's knots, held in place not by energy barriers alone, but by the mathematics of continuity. Topology also organizes the strange world of quantum condensed matter. The quantum Hall effect, where Hall conductance is quantized in units of E²/h, is classified by integers called Chern numbers. These numbers do not depend on microscopic details like impurities, but on the global topology of the electronic wave functions in momentum space. Change parameters smoothly, and the Chern number stays fixed, until the system undergoes a phase transition, at which point it jumps. This robustness is why the quantum Hall plateaus are so precise. They are not the fragile products of engineering, but topological invariants etched into the mathematics of the system. From this insight grew the broader notion of symmetry-protected topological phases. These are states of matter that look ordinary in bulk but harbour protected edge states that cannot be destroyed by local perturbations as long as certain symmetries remain intact. Topological insulators are one famous example, conducting only on their surfaces while insulating inside. Even if you roughen their edges or add impurities, the edge conduction persists because it is safeguarded by time reversal symmetry. These phases are the condensed matter analogues of locked safes. Break the symmetry, and you can dismantle them, but as long as the symmetry is honoured, they remain impervious to local tinkering. Finally, there are anomalies. subtle reminders that symmetry at the classical level does not always survive quantization. A system may respect a conservation law in its equations of motion, only for quantum effects to spoil it. One famous case is the axial anomaly in quantum electrodynamics, where a symmetry of massless fermions is broken by the quantum structure of the vacuum. Such anomalies are not nuisances but vital features. They explain why neutral pions decay into two photons, and they guide the construction of consistent quantum field theories. In some cases, demanding that anomalies cancel between different fields is the only way to ensure a theory makes sense. Symmetry, then, is not just about what is preserved. It is also about understanding the precise and sometimes surprising ways in which it can fail. Every measurement carries uncertainty, and combining several measured quantities requires careful bookkeeping. Propagation of uncertainties uses derivatives to see how small changes in inputs ripple into the output. For a result y that depends on variables x1, x2, the variance of y is approximated by the gradient of y dotted with the covariance matrix times the gradient transpose. In words, sigma sub y squared equals sum over I and j of partial y over partial x sub I times partial y over partial x sub j times covariance of x sub I and x sub j. If inputs are uncorrelated, this reduces to a sum of squares of sensitivities times variances. The method teaches you where precision matters most. The terms with the largest derivatives and variances dominate the budget, guiding smarter experimental design. Random scatter averages down, but systematic errors are stubborn. You cannot average away a bias. Systematics are offsets or distortions that push results consistently high or low, miscalibrated thermometers, zero shifts, scale nonlinearities, background leaks. Combat them with calibration and control experiments. Compare against reliable standards. Reverse the sign of signals, swap components, vary conditions that should not matter, and verify they do not. The mantra is, characterize, correct, and carry the residual as a systematic uncertainty. Averaging more data only sharpens the wrong answer if a bias remains. Calibration is the cure, not repetition. Human expectations can quietly steer choices in data cuts and models. Blind analysis techniques block that bias by hiding the answer until the procedure is frozen. You might add a secret offset to the final fit parameter, scramble event labels, or mask the signal region while developing selections on sidebands. Only after all choices are locked do you unblind and reveal the true value. This discipline prevents unconscious tuning toward a desired outcome and makes post-unblinding changes rare and well justified. In precision fields, from particle physics to medicine, blinding turns good intentions into robust practice. Extracting a whisper from a hurricane of noise is what lock-in detection does best. If your signal is coherent at a known reference frequency, modulate the source or chopper, then multiply the detector output by in-phase and quadrature reference sinusoids and average over time. Random noise, which has no fixed phase, averages towards zero. The coherent component integrates up. In words, the recovered amplitude scales with integration time, while broadband noise shrinks like 1 over the square root of bandwidth. This is why lock-in amplifiers can measure nanovolt signals buried beneath microvolt noise. They narrow the effective bandwidth to a sliver around the reference and keep impeccable time with the source. Oscillators, clocks, lasers, microwave sources do not just have one stability, they wander differently over seconds, minutes, or hours. Allen deviation is the tool that maps this. Computing the root mean square of fractional frequency differences between adjacent averaging intervals too. Plotting Allen deviation versus tau reveals regimes. White phase noise falling as 1 over tau, flicker frequency noise flattening, random walk rising as the square root of tau. This fingerprint tells you the best averaging time, the dominant noise processes, and whether improvements should target electronics, environment, or control loops. For timekeeping and navigation, Allen deviation is the truth teller across timescales. Every trustworthy measurement ultimately traces back to a common yardstick. Metrological traceability is the documented chain linking your instrument to international standards through calibrations with stated uncertainties. A lab thermometer is compared to a calibrated reference. That reference is tied to a national metrology institute, and those institutes agree on realizations of units like the Kelvin through primary standards. Each link adds an uncertainty contribution, and the full calibration certificate records them. Traceability ensures that a volt measured in one lab means the same as a volt measured anywhere else, turning local readings into globally comparable facts. When you are riding in a car, your body carries momentum in the direction of travel, even if you feel like you are just sitting still. In a sudden stop, that momentum does not vanish on its own. It needs an external force to change it. Without a seatbelt, that force might come from the dashboard or the windshield, applied abruptly and dangerously. With a seatbelt, the force is spread across stronger parts of your body and applied over a slightly longer time, reducing the peak impact. It is Newton's second law in action. The change in momentum equals force times time. Stretching out the time lowers the force, which is why that strap across your chest is not just a legal requirement, but a simple, elegant application of physics saving lives daily. Bicycles offer another everyday lesson in mechanics. They balance not because of magic, but because of a mix of geometry, gyroscopic effects, and rider feedback. The front wheel is mounted so that its contact point with the ground trails behind the steering axis, a geometry called trail. If the bike tips, the trail steers the wheel into the lean, helping restore balance. Gyroscopic precession of the spinning wheels also adds resistance to sudden tilts, though experiments with specially designed bikes show the geometry alone can stabilize them. Of course, the rider's brain and body close the loop, making constant micro-adjustments. Stability is not a single cause, but an orchestra of effects that keep two narrow wheels under control. Friction, too, hides a subtle story. Static friction, the grip between surfaces at rest, is adaptive. It can range from 0 up to a maximum value set by the coefficient of static friction times the normal force. As long as you push below this threshold, the object stays put and the frictional force simply matches your push. Once that threshold is exceeded, sliding begins and the system switches to kinetic friction, which is usually lower. That is why nudging a heavy box across the floor feels hardest at the start but easier once it is moving. Friction is not just a nuisance. It is also what lets us walk without slipping, hold objects securely and drive cars on roads. Microwave ovens transform kitchens using molecular physics. The oven emits electromagnetic waves at around 2.45 GHz, a frequency well matched to rotational resonances of polar molecules like water. The oscillating field tugs at the electric dipoles, setting them spinning back and forth billions of times per second. Collisions between molecules spread this motion into random kinetic energy, which we perceive as heat. Non-polar molecules like oils do not absorb microwaves as directly, but the heated water within foods conducts the warmth. It is why soups and vegetables heat quickly, while dry bread or oil warms unevenly. Your leftovers spinning in the microwave are literally warmed by molecular gymnastics. Induction cooktops are another clever use of electromagnetism. Beneath the glass surface lies a coil that generates a rapidly changing magnetic field. Place a conductive pan on top, and the field induces circulating currents in its base. These eddy currents dissipate energy as heat directly in the cookware itself, not in the stove. The efficiency is remarkable. The cooktop remains cool to the touch except under the pan, and energy goes almost entirely into the food. The catch is that the cookware must be ferromagnetic, iron or steel, so the magnetic flux couples strongly. Aluminum or copper pans only work if layered with magnetic material. In essence, your skillet becomes the heating element. Even windows showcase applied physics. A single pane is just a sheet of glass, but double-pane windows add a sealed layer of air or inert gas in between. This trapped gas conducts and convects poorly, reducing heat transfer. Low emissivity coatings further cut down on radiative heat exchange, reflecting infrared back inside during winter and outside during summer. The result is a barrier against all three modes of heat flow: conduction, convection, and radiation working together. By slowing thermal exchange, double-pane windows keep houses warmer in cold months and cooler in hot months. They are a silent energy-saving device built on nothing more exotic than layers of air, glass, and a dash of radiative physics. Radio waves, the giants of the electromagnetic spectrum, can stretch for kilometers in wavelength, and that sheer size gives them a unique superpower: diffraction. Long wavelengths bend easily around obstacles such as hills, buildings, and even entire mountain ranges, allowing radio signals to travel far beyond a straight line of sight. This is why you can still pick up AM radio while driving through valleys or around corners. The longer the wavelength, the more it hugs the terrain. Shorter wavelength signals like FM radio or television are more line of sight, which is why they fade more quickly when blocked. In a way, radio waves are like sound. Deep bass notes carry farther through walls while high-pitched tones get muffled. Microwaves, with wavelengths measured in centimeters, occupy a sweet spot for both communication and detection. Radar systems send out pulses of microwaves and measure the reflected signals bouncing back from aircraft, raindrops, or speeding cars. Because microwaves are short enough to resolve fine details yet long enough to penetrate clouds and fog, they are perfect for weather monitoring and navigation. The Doppler effect also comes into play. If the target is moving, the frequency of the reflected wave shifts, allowing radar to measure speed with extraordinary precision. It is the same principle as a passing siren changing pitch, only here it plays out with invisible electromagnetic ripples. Infrared light is just beyond the red end of the visible spectrum and carries the glow of warmth. Every object above absolute zero emits infrared radiation, with hotter objects glowing more intensely. Night vision goggles exploit this by detecting infrared light that human eyes cannot see, turning thermal signatures into visible images. Warm bodies stand out against cooler backgrounds, and even footsteps can leave a fading trail. Infrared is also central to remote controls, thermal cameras, and astronomy, where it reveals cold interstellar dust clouds invisible to ordinary telescopes. It is heat itself, dressed as light. Ultraviolet radiation sits just beyond violet light, with higher energy per photon. This energy is enough to break chemical bonds, which is why ultraviolet both enables and threatens life. On one hand, ultraviolet light excites certain materials into fluorescence, making them glow in dazzling colours under black light. On the other hand, the same bond-breaking action can damage DNA, leading to sunburn and mutations. Sunscreen works by absorbing or reflecting ultraviolet before it penetrates skin, while Earth's ozone layer provides a vital shield against the most harmful bands. Without it, life on land as we know it would be impossible. X-rays carry photons energetic enough to pass through soft tissue but not dense bone, creating shadow images that revolutionized medicine in the late 19th century. Their ability to penetrate depends strongly on atomic number and density. Carbon and hydrogen-rich flesh attenuates them weakly, while calcium-rich bone stops them efficiently. This contrast makes X-rays ideal for imaging fractures, dental health, and lung conditions. In physics and material science, X-rays also reveal crystal structures through diffraction, probing arrangements of atoms directly. They are not only diagnostic tools but windows into the invisible world of matter itself. Gamma rays are the heavyweight champions of the electromagnetic spectrum, with energies millions to trillions of times greater than visible light. They emerge from nuclear transitions, radioactive decay, and cosmic cataclysms like supernovae or merging neutron stars. Unlike X-rays produced by energetic electrons, gamma rays originate deep in nuclear processes. Their penetrating power is so extreme that shielding requires thick layers of lead or concrete. Astronomers use gamma-ray observatories to watch the universe's most violent explosions, while physicists rely on them to study the heart of matter. In gamma rays, nature broadcasts both its most destructive and most illuminating signals. When physics turns into numbers on a computer, the first step is discretization, replacing smooth, continuous functions with grids or elements that can be handled digitally. A derivative like di over dx becomes a finite difference where you compare values at nearby points and divide by their spacing. In 2 or 3 dimensions, this turns differential equations into vast systems of algebraic equations. Finite difference methods approximate derivatives directly, while finite element methods break space into small shapes, each with local trial functions that patch together into a global solution. The art lies in choosing how fine the mesh should be. Too coarse and you miss the physics. Too fine and the computer groans under the weight of equations. Even with discretization, not every step size is safe. The current Friedrichs-Lewis condition, often shortened to the CFL condition, sets a stability limit. Your numerical step in time must be small enough that information cannot jump farther across the grid in one step than waves can travel physically. If you break this rule, solutions grow unstable, blowing up with nonsensical oscillations. It is like trying to record a fast drum beat with a tape recorder that samples too slowly. The rhythm becomes distorted. Respecting stability conditions keeps simulations honest and prevents a digital explosion of nonsense. Some problems are too high-dimensional for grids. Integrals over many variables, such as those in statistical mechanics or quantum field theory, defy brute force methods. Monte Carlo techniques step in, using random sampling to estimate averages. The beauty is that the error decreases as 1 over the square root of the number of samples, regardless of dimensionality. This makes random walks a surprisingly powerful weapon against complexity. From predicting stock options to simulating particle collisions, Monte Carlo turns chance into precision by letting randomness do the heavy lifting. Spectral methods take a different approach. Instead of representing functions by local patches, they expand them in global basis functions like sines, cosines, or orthogonal polynomials. For smooth problems, spectral methods converge exponentially fast, meaning a modest number of terms yields astonishing accuracy. Fluid turbulence, quantum wave functions, and weather patterns can all be attacked with these expansions. The downside is that sharp features like shocks are harder to capture. Global functions struggle with sudden jumps. But when the problem is smooth, spectral methods are the precision scalpels of computational physics. Not every problem needs the full complexity of millions of variables. Reduced-order models aim to capture the essence by identifying dominant modes or patterns and discarding the rest. Think of airflow around an airplane wing. Most of the complexity is in a few coherent structures like vortices, while the rest is small-scale details. By projecting dynamics onto the dominant modes, simulations run orders of magnitude faster, while still reproducing the crucial behavior. This is like summarizing a symphony with its main themes. You lose some nuance but keep the story intact. Finally, every simulation must face two fundamental tests: verification and validation. Verification asks whether you solved the equations correctly. Did the discretization, coding, and numerics behave as intended? Validation asks whether the equations themselves match reality. Did you choose the right physical model? A program may be perfectly verified yet fundamentally invalid if the underlying assumptions are wrong. Checking both is essential, because there is nothing more misleading than a simulation that runs beautifully, produces colourful plots, and yet describes a world that does not exist. Verification ensures mathematics is respected. Validation ensures physics is respected. The sun is not just a source of light and warmth. It is also a restless star constantly blowing a stream of charged particles outward, known as the solar wind. When this wind collides with a planet that has a magnetic field, such as Earth, the field acts like a shield, deflecting most of the incoming particles and sculpting a protective cavity called the magnetosphere. Yet the boundary is not invulnerable. Magnetic reconnection events, where field lines snap and reconnect, funnel particles down toward the poles. There they collide with atoms in the upper atmosphere, exciting them and creating the shimmering curtains of green and red light we call auroras. It is cosmic weather, played out on a planetary scale. Moons, too, feel the power of physics in ways that shape their landscapes dramatically. Tidal heating is a process where gravitational stretching and squeezing from a parent planet continually flexes a moon's interior. This kneading generates heat, sometimes enough to power volcanism or maintain subsurface oceans. Jupiter's moon, Io, is the most volcanic body in the solar system. Its surface dotted with constantly erupting volcanoes fueled not by radioactive decay, but by relentless tidal tugging. Europa and Enceladus, though less dramatic on the surface, hide oceans beneath their icy crusts kept liquid by the same invisible hand of tidal heating. Atmospheres are fragile things, especially when a planet's gravity is weak or its temperature high. Atmospheric escape depends on the balance between the thermal speeds of particles, the planet's mass, and photochemical processes driven by solar radiation. Hydrogen and helium, being light, are the first to slip away into space, which is why Earth retains nitrogen and oxygen, but has long since lost its primordial hydrogen-rich atmosphere. Ultraviolet light can break apart molecules, giving fragments extra energy to escape. Over billions of years, these processes sculpt a planet's climate and even its ability to host life. Mars, once warmer and wetter, is today a dry, thin-air desert world because escape won the battle. Orbiting a magnetized planet can be hazardous thanks to radiation belts. These are donut-shaped regions where energetic charged particles from the solar wind become trapped by the planet's magnetic field. Earth's Van Allen belts are the most famous, discovered in the late 1950s, and they swell dramatically during solar storms, intensifying radiation hazards for satellites and astronauts. The trapped particles can spiral along magnetic field lines, mirror between poles, and gain even more energy during geomagnetic disturbances. These belts are both a protective barrier, keeping some radiation away from the surface, and a technological hazard, battering spacecraft electronics. On airless worlds like the Moon or asteroids, the surface is covered not by soil in the earthly sense, but by regolith, a loose layer of fragmented rock and dust created by countless impacts. Its properties matter enormously for landers and rovers. Fine grains can behave almost like a fluid, shifting underfoot, while sharp edges can cling stubbornly to equipment. Regolith also controls how heat flows. Without an atmosphere, day-to-night temperature swings are buffered only by how well the surface conducts and stores heat. Understanding regolith is essential for both safe landings and for predicting how these bodies radiate heat back into space. Even tiny forces can accumulate into cosmic-scale consequences. The Yarkovsky effect is a subtle push on rotating asteroids caused by the way they absorb sunlight and re-radiate it as heat. Because the emission is not perfectly symmetric, warmer afternoon sides radiate more strongly. It creates a small but steady thrust. Over millions of years, this effect can shift an asteroid's orbit, enough to move it out of the main belt or, in rare cases, nudge it onto a path that intersects Earth. What seems like an insignificant thermal hiccup is in fact a planetary-scale steering force shaping the trajectories of rocks across the solar system. The most accurate timekeepers humanity has ever built are atomic clocks, which anchor their ticks to precise transitions between energy levels of atoms. Cesium-133 atoms, for instance, define the second as 9,192,631,770 oscillations of microwave radiation, corresponding to their hyperfine transition. Optical clocks go even further, locking onto transitions in atoms like strontium or ytterbium at frequencies thousands of times higher than microwaves. Because more oscillations fit into each second, errors average out more quickly, making them stable to better than a part in 1 quintillion. In practice, that means such a clock would not lose a single second in the entire age of the universe. Einstein's general relativity enters the picture at scales that seem impossibly small. Gravitational redshift means that clocks run at different rates depending on their position in a gravitational potential. A clock on the ground ticks slightly slower than one raised a meter higher. In the best optical clocks, even lifting one by a few centimeters changes its measured frequency. Metrology labs have confirmed these shifts experimentally, effectively using clocks to measure height with millimeter precision. Time itself becomes a ruler, warped by gravity, and precision clocks turn into scientific instruments for mapping Earth's gravitational field. The global positioning system is an everyday application where relativity cannot be ignored. GPS satellites orbit Earth at an altitude of about 20,000 kilometers, and their onboard atomic clocks experience both special and general relativistic effects. Special relativity slows them down because of their orbital speed, while general relativity speeds them up because they are higher in Earth's gravitational potential. The net result is that their clocks tick about 38 microseconds faster per day than identical clocks on the ground. Without correcting for this, GPS positions would drift by kilometers within hours. Engineers solved the problem by pre-adjusting the satellite clock frequencies so that once in orbit, they keep perfect time with ground-based standards. To connect optical clocks to the established microwave world, scientists use frequency combs. A frequency comb is a laser that emits light not at a single color, but at a series of evenly spaced lines across the spectrum like the teeth of a comb. This allows optical frequencies, hundreds of terahertz, to be directly related to microwave frequencies of a few gigahertz. The invention of frequency combs was so transformative that it earned the 2005 Nobel Prize in Physics. These devices bridge the gap between technologies, enabling optical clocks to redefine the second and integrate seamlessly with existing timing infrastructure. Another secret to stable timekeeping is the use of resonators with exceptionally high quality factors, or high Q. A resonator's Q measures how long it can store energy relative to how fast it loses it. The higher the Q, the narrower the spectral line, and the more sharply you can lock a clock to it. Optical cavities, sapphire oscillators, and crystalline resonators all serve to narrow line widths and suppress noise. By confining light or microwaves in carefully engineered cavities, physicists sculpt precision tools that keep oscillations steady, letting clocks listen to the universe's tick with minimal jitter. Finally, when synchronizing clocks separated by long distances, simply sending signals back and forth is not enough, because asymmetries in travel paths distort the measurement. Two-way time transfer solves this by exchanging signals in both directions and comparing round-trip times. Since delays affect both paths equally, subtracting them cancels out the uncertainty, leaving only the difference in the clocks themselves. This method allows laboratories around the world to synchronize their clocks to within billionths or even trillionths of a second. From satellites to submarine cables, the careful sharing of time ensures that physics experiments, communication networks, and navigation systems remain in harmony across the globe. In living systems, physics quietly sets the limits of what cells can and cannot do. Diffusion, the random wandering of molecules, is the simplest transport process, but it comes with a catch. The time it takes grows with the square of the distance. That means if it takes a molecule 1 second to diffuse across 1 micron, it will take 100 seconds to cross 10 microns. This quadratic scaling makes diffusion efficient for tiny cells, but hopelessly slow for large ones. It explains why most cells stay small, why they rely on circulatory systems or molecular motors for long-range transport, and why the microscopic world feels so different from our own. Cell membranes are not just barriers, they also behave like electrical circuits. The lipid bilayer acts as a capacitor, storing charge across its thin insulating thickness, while embedded proteins act like resistors, allowing ions to flow through channels. Together, the membrane has an RC time constant, the product of resistance and capacitance, that sets how quickly the voltage across it can change. In neurons, this time constant helps shape the rise and fall of action potentials, the electrical spikes that carry information. Too short a time constant and signals decay too quickly. Too long, and the cell responds sluggishly. It is a balancing act between storage and leakage that underpins the physics of thought itself. Inside these cells, molecular motors hustle along in a way that makes city traffic look tame. Proteins like kinesin and dynein walk along microtubules, dragging vesicles full of cargo, while myosin marches along actin filaments to power muscle contractions. Their steps are not smooth clockwork but stochastic, driven by thermal jostling and rectified by coupling to chemical reactions. Each motor hydrolyzes molecules of adenosine triphosphate, or ATP, releasing energy that biases its movement in one direction. The result is a noisy stop-and-go procession, where randomness at the nanoscale is harnessed to produce directional motion at the cellular scale. Even genetic material is constrained by physics. A human cell must cram nearly 2 meters of DNA into a nucleus only a few microns wide. This packaging is possible only because DNA wins around protein spools called histones and coils into higher-order structures. But packing DNA is not free. It costs bending energy to curve the stiff double helix, and it requires counteracting the electrostatic repulsion between negatively charged strands. Proteins and ions work together to manage this energy balance, keeping DNA compact enough to fit yet accessible enough to be read and copied. It is the ultimate case of organizing a library in a broom closet. Vision begins with a quantum event so small it borders on unbelievable. In the retina, a molecule of retinal bound to a protein called opsin can absorb a single photon of light. That photon triggers an isomerization, a change in shape from a bent form to a straight one. This minute structural flip sets off a cascade of biochemical signals that amplifies the response until it becomes a nerve impulse sent to the brain. Human eyes can sometimes detect even a handful of photons in darkness, proof that biology has evolved to harness physics at its most delicate quantum scale. Blood, the river of life, does not flow like simple water. It is a suspension of red blood cells, white cells, platelets, and proteins, and this complex mixture makes it a non-Newtonian fluid. Unlike water, whose viscosity is constant, blood's viscosity changes depending on flow rate and conditions. At low shear rates, red blood cells clump into chains called rouleaux, making the fluid thicker. At higher shear rates, the chains break apart and blood thins, a property known as shear thinning. This behavior ensures that blood can flow through capillaries barely wider than a single cell, yet also resist too much turbulence in large vessels. It is rheology, fluid mechanics, applied to something as intimate as the pulse in your veins. Deep beneath our feet, Earth hides a natural power plant. The planet's magnetic field is generated by the geodynamo, a process driven by the motion of molten iron in the outer core. As the liquid metal convects due to heat escaping from the inner core, Earth's rotation organizes those flows into spirals through the Coriolis effect. Moving conductive fluid generates electric currents, and those currents in turn create magnetic fields, which reinforce the process. It is a self-sustaining loop that has kept Earth magnetized for billions of years. Without this invisible shield, solar wind would strip our atmosphere, leaving the surface as barren as Mars. Earthquakes, while devastating on the surface, serve as probes of Earth's hidden layers. Seismic waves ripple through the planet, and their speeds and paths change depending on the material they travel through. Compressional P waves can travel through both solids and liquids, while shear S waves cannot pass through liquid at all. This is how geophysicists determined that Earth has a liquid outer core. S waves vanish at its boundary, while P waves bend and slow. Reflections and refractions within Earth produce seismic echoes, which allow scientists to map the crust, mantle, and core in detail without ever drilling more than a few kilometers. Each quake becomes a natural sonogram of the planet. The greenhouse effect is sometimes described as a blanket around Earth, but the real physics is far more precise. Greenhouse gases such as carbon dioxide, methane, and water vapor absorb infrared radiation at specific wavelengths corresponding to their molecular vibrations. This process is best described line by line, as each gas has a spectrum of absorption bands. When infrared photons emitted by Earth's surface are absorbed, the energy is re-emitted in random directions, including back downward, warming the surface and lower atmosphere. Without this effect, Earth would be a frozen ball, but as concentrations of greenhouse gases rise, the balance shifts, trapping more heat. It is not a blanket. It is a molecular dance that changes the planet's energy flow. The oceans are Earth's great conveyor belts, redistributing heat and storing carbon across the globe. Surface winds drive currents such as the Gulf Stream, carrying warm water northward, while deep overturning circulation brings cold, dense water from polar regions into the abyss. Small-scale eddies stir and mix these flows, transporting nutrients as well as heat. This global circulation moderates climate, keeping Europe warmer than its latitude would suggest, and helping regulate atmospheric carbon dioxide levels. Disruptions in these patterns, such as a slowdown of the Atlantic overturning, could trigger dramatic climate shifts, showing how tightly climate and ocean dynamics are linked. Feedback loops in the climate system amplify or dampen changes, making predictions both challenging and fascinating. The ice albedo feedback is one of the most striking. Melting ice reduces reflective surfaces, exposing darker ground or ocean that absorbs more sunlight, which accelerates warming. Water vapor, itself a greenhouse gas, increases as temperatures rise, further amplifying the effect. Clouds add complexity, reflecting sunlight but also trapping infrared radiation depending on their type and altitude. Together, these feedbacks set Earth's climate sensitivity, how much warming occurs for a given increase in greenhouse gases. They turn a simple energy balance into a dynamic, interconnected system full of tipping points. To peer back in time, scientists turn to paleoclimate proxies, natural recorders of past environments. Isotopes of oxygen in ice cores reveal ancient temperatures, as the ratio of heavy to light isotopes depends on conditions when snow fell. Tree rings record growth variations year by year, sensitive to rainfall and temperature. Corals encode chemical signals of ocean conditions, while sediments at the bottom of lakes and seas accumulate layers that track climate rhythms. Together, these proxies extend our climate record back hundreds of thousands, even millions of years. They show that Earth has swung between ice ages and warm periods, and they place today's rapid warming in stark historical perspective. One of the most elegant demonstrations in physics involves dropping a feather and a hammer. On Earth, the feather drifts gently down while the hammer thuds to the ground, and it is easy to think gravity treats them differently. But the real culprit is air resistance. In a vacuum with no air to push against, both fall side by side, accelerating at the same rate under gravity alone. Astronaut David Scott performed exactly this experiment on the Moon in 1971, dropping a hammer and a falcon feather. To the delight of everyone watching, they hit the lunar surface simultaneously, proving in dramatic fashion what Galileo had reasoned centuries earlier. Gravity does not discriminate by mass. Many people imagine astronauts in orbit as experiencing zero gravity, but this phrase is misleading. Gravity at the altitude of the International Space Station is only slightly weaker than at Earth's surface, about 90% as strong. The sensation of weightlessness comes instead from continuous free fall. This station and everything in it are falling toward Earth, but because they also have tremendous sideways speed, Earth curves away beneath them. The result is a perpetual fall around the planet. Astronauts float not because gravity is gone, but because everything around them is accelerating together. It is gravity's grip, not its absence, that makes weightlessness possible. The concept of centrifugal force is another common point of confusion. When you spin a bucket of water and see the water pressed outward, it is tempting to think there is an outward force pushing it. In reality, in an inertial frame, the only real force is the inward centripetal force from the bucket walls, keeping the water moving in a circle. Centrifugal force appears only if you adopt a rotating frame of reference, where it acts as a so-called fictitious force to balance equations. It is not a fundamental interaction like gravity or electromagnetism, but a bookkeeping tool to make rotating coordinates easier to describe. The water clings to the sides not because of an outward push, but because it resists the constant inward tug. Movies often portray space battles with fiery explosions that echo like thunder, but the reality is quieter, completely silent in fact. Sound is a mechanical vibration that requires a medium like air, water, or solid matter to propagate. In the vacuum of space, there is nothing to carry those pressure waves. A spacecraft explosion would flash brilliantly with light, scatter debris at high speeds, and release radiation, but an observer nearby would hear nothing. Inside the ship, however, vibrations travelling through its structure could certainly be heard. It is a good reminder that sound is local, while light can cross the cosmic void with ease. Boiling water at room temperature may sound like a contradiction, but it is entirely possible if you lower the surrounding pressure. Boiling occurs not at a fixed temperature, but when the vapour pressure of the liquid matches the external pressure. At sea level, that happens at 100 degrees Celsius, but in a vacuum chamber, water boils vigorously at 20 degrees or even lower. This is why your blood would not freeze in space, but could start to boil in exposed tissue. It is also why pressure cookers work in the opposite direction, raising pressure so that water boils at higher temperatures, speeding up cooking. Temperature and pressure are dance partners in the physics of phase transitions. Finally, it is worth dispelling the notion that cold is a substance that seeps into things. Cold is simply the absence of heat. Heat flows spontaneously from regions of higher temperature to regions of lower temperature until equilibrium is reached. Temperature itself measures the average kinetic energy of particles. The faster they move, the hotter the substance. When you touch a block of ice, it does not pour coldness into your hand. Instead, your faster-moving molecules lose energy to the slower-moving molecules of the ice. Cold is not a thing in its own right. It is a way of describing less energy, less motion, and less warmth. Physics shows us that what we feel as cold is simply the direction heat decided to go. If you've made it all the way to the end of this journey, then congratulations. You have officially survived 300 physics facts. That alone deserves an award. In fact, after absorbing all of this, you might just qualify as an honorary physics professor, or at least the friend who always has a fun science fact ready at the dinner table. Thank you so much for sticking with me through this marathon of motion, energy, particles, and the universe itself. If you enjoyed it, please give the video a like. It really helps the algorithm know that this kind of content is worth sharing with more people. And if you are not already subscribed, I would love to have you join the Sleepy Scientist community. Be sure to click the notification bell too, so you never miss the next upload. And finally, if there is a topic you would love to see covered in a future video, whether it's another deep dive into physics or a completely different corner of science, please let me know in the comments. Thanks again for watching, and until next time, may your nights be restful, your curiosity endless, and your dreams filled with the wonders of the universe.